Final podium test, line check for webcast and recording. Good. All right, I'm going to move on to the lives. Check, 1, 2, 1, 2. And visually the level, check 1, 2, 1, 2. Good afternoon, this is a line check for the webcast and for the video recording. Check 1, 2. All right, this live's going down. I'm gonna open up the next one. Settings are same here, so I didn't bring it up for you. Check 1, 2, 1, 2, 1, 2, 1, 2. January, February, March, April, May, July, August, September, October, November. Check 1, 2, 1, 2. 1, 2, 2, 2, 2, 2. Back there, check you guys. Check. Which channel is this on? Check 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Check. 1, 2, 1, 2, 2. What's what here? Is this the podium? DI? Oh, that's for cloud. Okay, check. 1, 2, 2, 2, 2, 2. Check. 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Well, that explains that. Check 1, 2, 1, 2, 1, 2, 1, 2. Hey, check. Live, check 1, 2, 3, 4, 5, 6. Rick, let me adjust here first. 1, 2, 3, 4. 1, 2, 3, 4. Check. Live, check. Hey, 1, 2, 3, 4, 5, 6. Sibilance, 8. Final test. Is that good for you? Okay.
Whatever you did.
I'm gonna actually go back to the other live really quickly. And the buzz is gone?
Yeah, it's gone.
You sure?
Yep, it's clean.
Okay. Let me see.
Verification, but I think it's gone. It's gone.
Check. Yeah.
Yep. Okay.
All right, let me get that other live back. Hey, check. I knew it. Check. This guy doesn't know what he's doing. Check. Hey, 1, 2, 1, 2. Live 1, final test. Live 1, final test. Check. The buzz is back. Check 1, 2, 1, 2. Hey, check 1, 2, 1, 2, 1, 2. Okay, so basically That's what it is. I don't know
Yeah.
why, but
Okay.
hey,
That's
check.
a copy. Okay.
Final check for webcast and live. Check 1 2 1 2 1 2. Check check 1 2 3 4. Check 1 2 3 4. Check check 1 2 3 4. Sibilance. Hey, check 1 2 1 2 1 2. Does that sound okay?
Yeah, it's out fine, but the bus, because you have both labs on. Yeah. There you go.
Let me try something else.
Sure, go ahead.
Check check. Anything there? Any change? Any change?
Sound of a common change. It's
Change.
very noticeable on the bus.
Hey hey. Worse? Better?
Better. Now it's back.
Then it's got to be something oscillating or inducting. If I just go to the single, check 1 2 1 2 1 2. Hey,
definitely.
check check check. 1 2. Why are we pushing that up like that? Hey, check 1 2 3 4 5 6. All right, lob 1 seems to be cool. Yes.
Yes.
All right, we're gonna cut that out. Final podium test for room and feed. Check 1 2. You're good on the feed. Okay. Got. Am I? One sec. Final podium mic check. 1 2 for line. Line's good. Antone, if you would be so kind as to give this one, push this one up to like +5. Get a little bit more in the room. Check 1 2 1 2 1 2 1 2 1 2. I hate the sound of my voice too. Check 1 2 1 2 3 4 5 6. Sibilance 8. Check 1 2 1 2. Antone, push. Give me a little bit more. 1 2 1 2 1 2 1 2. Check check check. 1 2 3 4. Right there. Thank you. Check, 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 check. Hey, 1 2 1 2. Okay, now we're going to open up the second one just to see if we get that induction. Check 1 2 1 2 1 2 1 2. So that's it's clean. Awesome. There we are, gentlemen.
Could I have everybody's attention for one quick minute? We're going to start pretty close to 1 o'clock because we're going to broadcast this, this symposium, but I wanted just to pass on just some housekeeping issues. There are two cameras. One of the cameras is focused on the screen, and one will be focused on the speaker. So if you wander over here, you're probably off camera, and they can't hear you. So I'm going to ask the speakers, I know it's hard because I'm a walker too, but to stay near the microphone. The other thing I'm going to ask is when questions arise from the audience, if you could just repeat the question, because we don't have a traveling mic and the people on the other end of the broadcast may not hear the question. So before you answer it, if you would just repeat the question so it's part of the broadcast, I'd appreciate that. The order will be, Howard, you'll go first today, okay? And then, Rich, I'm going to let you go second. And then we'll move back into the order we went through this morning. So we're pretty close, another minute or so, and we'll go ahead and get started. What? Howard? You're number 3, Paula, okay? I'll come and tap you on the shoulder. And I want to thank you all for coming. I'll repeat this when we go live, but we did do a congressional briefing this morning, and we had probably close to 50, 55 people at the briefing. We had Yeah, I will. You're right. Almost. I think we're going to start here in a minute. Is it 1 o'clock? Okay, we're going to go ahead and start. You're going to hear a lot of this again that I went through this morning. And the speakers, the green line button is the pointer. It's green, and then these 2 arrows make it go forward and back. Okay. Okay, you can go ahead and turn those on. Tell me when. Oh, we're on now? Okay, good. All right. So I want to welcome everybody to the 2012 Association of Ecosystem Research Centers Research Symposium. The theme this year is the role of ecosystem science in national security. We're very fortunate to have 5 eminent speakers that will present presentations today. We're trying something new as an association this year, and that involves broadcasting this not only live, but we are recording this so it'll eventually live on our website, so those that can't see it today will have access to it in the future. I want to thank the speakers for allowing us to do this as well. So the Association of Ecosystem Research Centers was chartered back in 1987, and we've been doing these things for about, well, several decades, including the congressional briefing. The way it typically works is on these days we do a congressional briefing in the morning that's typically closed except to congressional staff. And then we follow that up with a research symposium where our speakers take more time to go into more depth about their topics in the afternoon, and that's where we are today. Our major objectives as an association are to advocate for ecosystem science, disseminate information, and provide education. I guess I should have introduced myself. My name is Dave Smith. I'm from the University of Virginia, and I'm the president of the association this year. We have a strong reputation in the community and also on Capitol Hill, providing an unbiased source of solid scientific information. And I think as an association, we're very proud of that, and we've done that again today. The theme, the role of ecosystem science in national security, was chosen by the board and the membership, and it really builds upon our briefing last year, where the theme was the importance of ecosystem services in the 21st century. We made an effort last year to try to incorporate the intersection of social science and natural sciences together, And we're going to continue to follow through with that by today's research symposium. The drought this year, the effects it's had on food production, our ever-increasing need for energy, and the emergence of significant environmentally related diseases, in fact, make this a very timely choice of topic. So on behalf of our member institutions and the AERC board, I want to welcome you here today. I will briefly introduce each of the speakers before they speak, so you know a little bit about their background. For those of you who are here in the audience, I think there's on the table out in the lobby, there's some information about their bio as well as their abstract. And for those that are listening online, you can get that same information on our website for this program. Our first speaker today is Dr. Howard Purcell. Dr. Purcell works at the Earth Systems Analysis Department at Sandia National Labs in Albuquerque, New Mexico. Dr. Purcell's presentation is entitled Human Ecology, Human Resilience, and Human Security. His work focuses on sustainability and resource management with an emphasis on links between ecosystems, economics, and security. And of special interest in his work is the relationship between resources, populations, ecosystems, and human security. With that, Howard, the podium's yours. Let me see if I can pull yours up. Which one's yours? Here. There you go.
That should do it. Oh, here it is.
Okay.
Just, yeah, click right there. Oops. Cancel that. There we go.
There you go. Sorry.
Okay, thank you, Dave. Thank you to the AERC. Thanks to all of you. May I ask who attended this morning? Anybody? And oh, lots of people. And so how many of you or how many people are scientists of one kind or another? Would you also raise your hand? Okay, great. So I'm going to basically make the same talk I made this morning, sorry, but I'll go more slowly and go into more detail, and I'll skip over a lot of the front-end stuff that, that might be a little bit less relevant to this audience. My co-authors, the people I've worked with this on, Len Malchinsky, Risa Mongello, Marissa Reno, Daniel Villa, and a lot of other people over the last year and a half or so. The work that I'm describing now is work that's been funded internally by Sandia National Labs and most recently by the National Intelligence Council. So we're hoping that this work is going to be in the next Global Trends 2030 report, which is coming out sometime after the election. So when we talk about ecology in general, people think about things like this. And however, a large part of ecology now is also this. And our argument is, and I'm going to go kind of quickly through this top stuff this time so that I can get to the stuff that I missed this morning, that I skimmed over very quickly this morning. The principles that drive these systems are the same principles that drive these systems. And so we're trying to apply basic ecological studies to human systems. And in so doing, we have noticed that there are three trajectories playing out in human history. They're very, very important. They're very slow to change, robust, long-term trajectories have been going on for hundreds of years, not going to be easy to turn or change. One of them is human population. I think Paolo is going to put up the same, a very similar slide. We're going to see this a couple times actually today, something like this. So we've got the year 0, the year 2000, and this dramatic exponential curve. This is an extraordinary dynamic going on the planet, I think. And we tend to overlook it. This might be an example of the frog in the pot, boiling the frog in the pot, that the temperature goes up very slowly and the frog doesn't notice. It's a horrible analogy, I know, but something like that seems to be going on here with human population growth on the planet Earth. A very important distinction that ought to be made. Well, an important point that I'd like to make is that this has changed recently. The UN had a previous projection for the year 9 billion people by the year 2050. About a year ago, they came out with this new population, which has this new projection, which has population going to over 10 billion by the year 2100, which is really a lot of people. We have a little over 7 billion people now, so increasing dramatically in the rest of this century. Where are we going to put them all? How are we going to feed them? Where are we going to get energy for them? How are we going to absorb the wastes? An important point, I think, to be made is that small variations in fertility can produce major differences in the size of the population over the long run. So specifically, here's the projection that I just described to you. And the report shows that if we reduced on a global level the fertility by 1/2 child per family below this level, then instead of peaking in 2100, not even peaking, but instead of hitting 10.1 billion in 2100, we would peak somewhere in between 2050 and 2100, and then decline again. Population would decline again to about 6.2 billion by the year 2100. So that's a way better outcome than this outcome here. And however, in order to achieve that, we have to put the subject of population growth control on the table as a subject for governments and citizens to discuss, and right now it is just such a politically sensitive issue that we can't even talk about it. However, if we could begin to address something like this, then we could have a very, very, very important impact on what future generations see on the planet, I think. So I said that there were 3 big trajectories playing out in human history. One is human population growth. Another is increasing resource consumption of all kinds. So here's energy. We see energy increasing across all different categories, except for nuclear right now. Energy increasing across all different categories, oil consumption increasing, electric power increasing, and this is both in absolute terms and per capita terms. Food, fertilizer, other speakers are going to talk about this subject, about how more affluent cultures like to eat higher on the food chain, meaning they want to eat more meat, more dairy, which has more water imbued in it. World and U.S. beef consumption, meat consumption in China and the United States, fertilizer, global kilocalories just going up. Isn't that remarkable? Increasing water consumption. As we want to grow more meat, it's going to take more water. Growing more food is going to take more water. Here is water use for energy production. A lot of work on this subject goes on at Sandia National Labs. And water is one of those categories in which, in some places around the world, in my hometown, per capita water consumption is going down, but population in the Middle Rio Grande Valley in New Mexico keeps going up. So absolute consumption continues to go up. And that's a dynamic that's true in many places of the world. So the 3 dynamics, one is population going up, one is resource consumption going up, and one is resource availability going down. So here's arable land per capita going down. It's just a function of population. There's a limited amount of arable land. And so as population goes up, arable land per capita goes down. Water, same deal. Water is going down as per capita. Water is fixed. There's a certain amount of water from year to year. It's highly variable, but overall the amount of fresh water that's available to us right now is fixed. So as more people come onto the planet, then there's less water per capita. Forests are declining all around the world. We all know about that. Biodiversity is declining, and some of the other speakers will discuss this at greater length. Grain stocks, fish stocks, all of these very, very important resources on the decline. Atmospheric resilience, this is the CO2 data from Mauna Loa in Hawaii showing the CO2 concentrations going up over time, which is really, in my view, a signal of the decreasing resource availability, that resource being the atmosphere's ability to absorb human wastes. So, and then lastly, and something that might be familiar to all of you, is ecosystem services. The ecosystem services in general are being impaired all across the biosphere: freshwater delivery, atmospheric composition, energy, waste disposal, and so on. And I think you are all familiar with this topic, so I will not belabor this one. So here's here's our premise, and there's a lot of ideas here on this one page. We're arguing that the decline of human ecological conditions creates tension. It makes systems more fragile. It makes the human systems more fragile. So they're more friable, they're more easily broken. So you have this fragile system because there's not enough food, there's not enough water, there's too many people, overcrowding, too much disease. Everything is very fragilely balanced, and some shock comes along, and the shock can come along in many, many different forms. It could be an economic collapse, it could be an ethnic clash, it could be a military invasion from the neighboring country, it could be migration from another country into your country, whatever. This could take many, many different forms, but because the system is so precariously balanced, it cracks. And then you have more conflict, and that conflict leads to greater decline of the human ecological conditions, and it creates this positive feedback loop that's actually very negative and can, lead to this downward spiral. Now, so we are trying to isolate the role that the human ecological condition plays in all of these dynamics. And we are not arguing that by solving the ecological issues we can solve all the conflict problems in the world, far from it, because there are all kinds of actors and influences out there that are sufficiently distant from ecological conditions, like despotic dictators, ethnic and religious extremists, poor governance, poverty, things that are separated from the ecological conditions that cause conflict too, and cause a lack of resilience and cause fragile, friable systems. But we think we can better understand causes and effects and better understand mitigation strategies for reducing the threat of conflict in the world by looking closely at the role that ecosystems and human ecological conditions play in them. So let me talk a little bit about resilience. Here is a picture of resilience. We hypothesize that all complex systems oscillate. And of course we can't test it because we can't test all complex systems, but that's a starting point. All systems are oscillating all the time. And it's all very relative. I'll say more about that in a minute. Resilience and sustainability, I think, are almost the same thing. And as I said this morning, it's not really clear in my head exactly whether they're the same or how they're or whether they're different or how they're different. And I'd be happy to explore that with anybody who wants to explore that later on in a discussion. But they're very, very closely related, resilience and sustainability in terms of ecosystems and ecological conditions. So for example, well, now this resilience is relative. So this curve could describe freshwater availability, highly variable from year to year over time, peaks and troughs, lots of valleys. But it's relative because while the overall system may be resilient, the overall system is going to proceed from left to right, and it's going to rebound, and there will be water next year, no matter how little water there was this year. But it's relative to the human need or the human demand for these resources. So here, if there's a human demand for this resource, and this happens to be fresh water, and it can't survive this trough, then we have a problem. Then we have the system fracturing because it's fragile, and maybe conflict ensues. Here's another example of a system that is non-resilient. That would be a species system. When a species becomes extinct, it disappears, and so that's not a resilient system. There's no breaking really that takes place, but the system, the species becomes extinct, and then maybe the larger ecosystems break. And then another event that can occur as these oscillations occur is a conflict event. And so what we're thinking about is that we humans want to dampen the oscillations that occur in the natural world. And a perfect example of that is hydrological systems. They flood, they go to drought, they mess with our economic systems. The floods flood our ag fields, the droughts hurt us in other ways. And so we want to dampen the oscillations. We want to stop the peaks, and we want to stop the deep valleys. That's what we do with dams in hydrological systems. And I think we should be, if we start to see our human systems as constantly oscillating, then we might apply the same kind of thinking to those human systems. That is, we want to avoid the big peaks, and we want to avoid the big troughs. And I'm thinking of that human growth curve that I showed right off the bat. That is, what's going to happen to that curve? Nobody knows. If it turns suddenly, it's going to mean a lot of people dying, a lot of people suffering, lots of chaos around the planet. That's something none of us want. So if we could learn to dampen these oscillations, these wild oscillations, before they hit their peaks and before they hit their troughs, we would be ahead of the game. So here's our working hypothesis. Systems with poor human ecological conditions are less resilient to shocks and more prone to collapse and conflict, and we're defining human ecology in the same way we would define any other ecological system, that is by the species that are in it, the way they interact, their population growth rate patterns, their population densities, disease, resource availability, consumption, and the ecosystem services that go with it all. And we're saying that by building these analytical quantitative tools, we might be able to help reduce some threat of conflict in the world. So, what are we doing about it? We have put together this thing we call the Human Resilience Index and Modeling Project, and we set out to isolate the impact of the human ecology on conflict. We set out in a very reductionist way to see if we could figure out what kind of signal does human ecology play in the evolution of conflict in the world. So we were extremely limited by the data that were available. We wanted data from a lot of countries for a lot of years. It wasn't easy to find data. We experimented with many different sets of indicators. At one time we had 29 different indicators in the index. We finally pared it down to something that we think is way more, certainly way more parsimonious and captures most of the big dynamics that we're interested in. Population growth rate, caloric intake per capita, renewable fresh water per capita, arable land per capita, median age, population density, and population health, which includes all of these three things rolled together: lifespan, infant mortality, child mortality. So we capture some population dynamics here. We capture the youth bulge to some extent here. Resources here. You might notice that there's something missing from this. The quintessential component of ecosystems, arguably, energy. And we cut energy out early on because we thought it was so closely connected to economy. But one could also make the same argument about food, as I think Molly will make later on today. So anyway, it's an imperfect mix, but it's, it's the way we've approached it all so far. Here is the equation that shows the calculation for the HRI, the Human Resilience Index. Very, very simple. The indicator value for a particular country, for a particular indicator, minus the average indicator value for all the countries, divided by the standard deviation of the indicator value across all the countries. The weighting is 1. It's equal across all of the different categories because we're trying to keep this as simple as we can. No hocus pocus, nothing buried down in the code. Transparent, easily to understand by policymakers and citizens. So we sum it all up and we get the HRI. There is one weighting issue. Some of these things are negative and some of these things are positive. So things we judged to be detrimental to the human ecology are subtracted. The things we judged to be positive are added. So population growth rate is subtracted. Population density is subtracted. I think everything else. Some of these are subtracted and added. But basically that's the way it works. So we're trying to balance things out. We've got 3 different scenarios that we worked on in this approach. One is the historic index, which is calculated for 154 countries, 1961 to 2008, using real data from that period of time. And I'll show you some of that in a minute. Then we did a non-dynamic projection, which just basically takes the projected population growth rate to drive all of these per capita values. It drives median age. The UN population projections drive these terms as well. And the only thing we fiddled with was caloric intake, and I'll leave that for later on if anybody's interested in how we did it. But anyway, that's a static, non-dynamic, basic projecting the HRA out into the future with population growth rate, projected population growth rate being the driver. And then what we're really focused on is the dynamic projection. We're trying to build a dynamic model of the world that allows us to model the HRI out into the future, given various perturbations or mitigation strategies that we might program into the model. So here are some of the results. So this is the historic HRI, 1961 to 2008, the 15 highest risk countries. Now I'm going to explain in a minute why these are not the lowest scoring countries, but we call them the highest risk countries. But you can see here they all are named here. So they're all countries you would expect to see on this list. We're not trying to rank the worst scoring countries or the highest risk countries in the world, because everybody knows what they are and where they are, and there's dozens of indices out there that are doing that. We're trying to build a model that captures the dynamics that allow us to better understand what's going on. So here you see some of these wide oscillations. Here's a big oscillation in Somalia, not culminating, but corresponding to the invasion of Ethiopia in 1977. A big dip on this black line. This is Malawi, corresponding with food riots in 1988. Here's a big dip in Afghanistan, corresponding to the fall of Kabul and then civil war a year later. So we're not talking about cause and effect. We're not trying to say that there's cause and effect here. We're looking for correspondence. We're seeing if this set of indicators and this index corresponds with events in the world, with conflict events in the world, and if one or the other might be an indicator of the other. And just for comparison, here is the historic HRI, same time period. These are the lowest risk countries, and you can see they're higher than than these. A whole different set of countries, all countries you would expect to see here. Less variability amongst the lower risk countries than in the higher risk countries. In fact, it's about a factor of 2, so this is twice as variable as this. So these are the kinds of things that give us a little bit of confidence in the model. The fact that it returns sensible results, the fact that the lower risk countries are less stable than the higher risk countries are less stable than the lower risk countries. Those are the kinds of things that gives us some confidence in the model. Here's another set of curves showing where declines in the index value correspond to conflict in other places in the world. Now, let me say that we are not able to capture every conflict event with this HRI, and the HRI shows some declines, some places where there is no conflict event associated with it, so it's far from perfect, but we think at least it's picking out some of these events, so we think that we're on to something. Here's a calibration curve. This shows, this is the graph you've already seen. This is 1961 to 2008. There's the Somalia invasion of Ethiopia and so on. And here is the dynamic model running out into the future, starting with 1961 values and then running out dynamically. So in the dynamic model, everything is interconnected. And so water availability goes up, and per capita food goes up because the water availability went up, and because the per capita food goes up, the growth rate goes up, and the growth rate goes up, so the HRI goes down, and so everything is just constantly shifting around in the dynamic model. And that's what we're trying to do, is build this dynamic model that will reflect these real conditions in the world, and which may then help us forecast where conflict is more likely to occur. Here's another test we made of our data to see if we could be more certain that we're really getting real results, and that is, this is the Uppsala conflict data set, which is a massive data set on conflict in the world, and this shows some nice correlation between the HRI value and conflict. So the higher the HRI value goes, the lower probability of conflict there is, and that is based on this big data set developed by the folks in, I guess it's Sweden. So here's a case study. We tried a bunch of case studies, and some of them didn't really work out. Here's one that worked out in a fairly illustrative way. This is Somalia. It's the worst scoring, it's the highest risk country of all. And so this green line represents the dynamic model results for Somalia from 2009 out to 2030, so still declining. No variability in this, by the way, just because of the dampening effects of all of the modeling that we're doing. And besides, we can't model, there's a lot of exogenous stuff that we're not modeling. We're not modeling other kinds of conflict events in the world. We're not modeling droughts or famines or spikes in food prices or anything like that. So it dampens out all the variability. So here's the decline. It puts it, these other gray lines are all the other 14 worst, highest risk countries. And so you see Somalia in 2030 is below them all. This is Burundi. And so we asked ourselves, well, what would it take to improve Somalia's position in the world? What would it take, say, to move Somalia's position up above all the other 14, move it up 14 places in the final calculation. And so we tried a few things until we got something that did it, and this is what we came up with. So the non-dynamic model is in red, the dynamic model is in black, and that tests what if we increased caloric intake, water, and arable land by a factor of 2. So multiplied the availability of all of those crucial resources by 2, which is a completely unreasonable thing to do. We don't know how to do it. We couldn't do it. We certainly couldn't do it in a year like we did here in the model. But that's what we did in the model, and that's what brings Somalia's score up above the other 14 lowest scoring countries. And then we said, well, what kind of change in population would it take to make the same kind of change in Somalia? And it took a 90% reduction in population. And this is very sudden, of course, in the model. But it pops that, it's that purple line, so it brings that HRI up above all of the other 14 countries. And then you'll note that these all start to decline again because that's the influence of population growth kicking back in. So it's the same population growth rates a year after the perturbation occurs. And so those kick in and the decline begins again. So what good is this? I think what it starts to do is it starts to put quantitative boundaries on the carrying capacity, maybe, of the region, on the relationship between human population and the resource base. It starts to allow us to bracket some of those relationships and put numbers to them where otherwise it's difficult to put numbers on them. And maybe this would be useful for policymakers and strategists in the region. And in fact, we're starting to work with an organization in the Horn of Africa that's interested in using this all as a conflict early warning system. You know, I'm reluctant to get into this because it's really down in the weeds. But let me say that the highest risk countries that you saw a minute ago in those curves are not the lowest scoring countries. Let me show you why. Look who turns up in the here, look who turns up in the 2008 HRI as the 10th lowest scoring country, Singapore, and the United Arab Emirates at the very top. So neither of those countries are perceived as countries that are at risk of failure. And so in our early results, we used to put this up, and we'd say Singapore in some of our results was right there in #1 spot, depending on which version of our model we were running. And people would say, oh, well, this thing is broken. How can you put Singapore at the top of your list? It's not the highest risk country in the world. And indeed, it's not, but it may be 10th in the world in terms of the risk associated with its human ecological condition. That is, Singapore has essentially no arable land. You know, it's a city-state, so that's another big difference between Singapore and all of these other things which are countries. But Singapore, so it's very, very small. It has no arable land. The only fresh water it has is essentially what falls out of the sky. And it's got a very high population density. And so, ecologically speaking, it's way out on a limb. And so it seems appropriate to me that Singapore should be on the list. But we don't want to go around the world saying Singapore is one of the countries at greatest risk of failure on account of its human ecological conditions. So we apply this filter with using the failed states index. You could use any index to filter this, but we use the failed states index. So these are countries, the countries in yellow are the countries that are in common between the 2008 failed states index and the 2008 human resilience index. And so those are the countries that we identify as the countries at greatest risk of failure on account of their poor human ecological conditions. And we could spend more time talking about that. I'm looking for Zimbabwe, Eric, and I don't see it right now. Okay, there you go. And that's the failed states index. But see, so what our work would suggest is that Zimbabwe may be at a high risk of failure, but it's not significantly on account of its poor human ecological condition. There are other factors contributing to its risk of failure. So it gets a little convoluted, I know, but we're not trying to fool anybody. And here are all the different results from all the different models. The 2008 historic, you've already seen that. The non-dynamic results. This is the dynamic results before the filter. So there's Singapore. And then these are the results after the filter, and so Singapore drops off, and these are all countries you would expect to see there. This is just a picture of the way the model actually looks. It's a model built in a system dynamics environment. Everything is interconnected. This is one very small section of the model. The model takes up many, many pages that look kind of like this. This is actually built in VenSim. We work in PowerSim. But it just gives you an idea of how all the different pieces are connected through other pieces. And with that, I'll stop. So thank you very, very much for your attention. I'll be happy to address questions if there are any, or talk to people afterwards, or write to me if you want to. I'd be happy to interact. Thank you very much.
So I'm going to ask Howard to stay up for a minute and entertain some questions. Is there any questions here from the audience? Yes?
Have you validated the model or thought of ways to maybe which you could validate the model?
Well, I guess the answer would be no in the strictest sense of the term validate. We have tried to validate it in the sense that we checked it. We tested it against the Uppsala data. We tested against the historical data. But in other ways, we have not done any validation. Now, one way to validate it would be to make predictions with it and then see if the predictions come true. And we're hoping to move towards that. You know, one idea that I skipped over and I would like to raise, if you look at these curves, if we were collecting data on these variables in real time, and we started to watch this curve plummet in real time, so this takes place over about 6-7 years, this dive from this point down to this point, then this might be an early warning indicator, something suggesting that there's something brewing in this region of the world. And another thing that we've discovered, or come to, it was not a great discovery, was that when you do this across when you use the entire country as your object of study, sometimes changes just wash right out. So in other words, we tested a drought in Afghanistan, but Afghanistan as a whole has lots of water in it. There's some parts that are very dry, some parts that are very wet. So hitting Afghanistan with a big drought doesn't change the Human Resilience Index value that much. People are very spread out. There's other things that Afghanistan has going for it. However, if we were to look at provinces in Afghanistan, separate provinces, then we think that we would be able to pick out which provinces are at greater risk of some kind of instability on account of the drought than others. And so we would be able to pick out more localized effects, and that's some of the kind of stuff we're moving towards. So if, as we move forward with all of this, that might be a way of moving towards some kind of validation.
Any other questions? Thank you, Howard.
Thank you, David.
And his email was on the screen, and he's more than happy to entertain questions after the fact. So the next speaker today is Dr. Richard Orsfeld, who's from the Carey Institute of Ecosystem Studies in New York. His research focuses on ecological determinants of human risk of exposure to infectious diseases, emphasizing Lyme and other tick-borne diseases. His presentation this afternoon is entitled Environmental Change, Infectious Diseases, and Biosecurity. And with that, I'll turn it over to our speaker. Let's see. There it is. There you go.
Thank you. Let's see here. Great. Well, thank you very much, Dave. Thank you all for coming. So my presentation is a little bit of an outlier in the sense that it has less to do with ecosystem science and more to do with community ecology, population ecology, and the like, but I think it impinges on ecosystem science as well. We know that natural ecosystems provide for our security in the form of water, food, and energy. But what's far less well appreciated, less well understood, is how natural ecosystems provide for our health security in the form of protecting us from exposure to various infectious diseases. So we also know that there are certain changes, environmental changes, insults to environments, environmental degradation and the like, that can compromise the ability of these natural ecosystems to protect our health against exposure to infectious diseases. And what I'll do this afternoon is describe a couple of case studies, case systems, in which environmental insults, environmental changes, clearly compromise the ability of natural ecosystems to maintain the security of our health systems. And the three different environmental changes that I'll be talking about, the three different disturbances, are invasive species, biodiversity loss, and climate change. So let me start with invasive species. A recent estimate of the impact, the financial, the economic impact of invasive species on US taxpayers came up with this impressive figure of $120 billion per year in the United States alone. Now, this estimate did not take into account the impact of invasive species on our disease in terms of infectious organisms. And that's because that research outlining the impact of invasive species on infectious diseases had not yet taken place when this estimate was made. There are now new data for at least a couple of tick-borne disease systems demonstrating that invasive species can have a very strong impact, increasing our risk of exposure to at least 2 different tick-borne diseases. In the case of the black-legged tick, I will show you some information in a moment showing how invasive species influence our risk of exposure to Lyme disease. And in the case of the Lone Star tick, the data show an increase in our risk of exposure to ehrlichiosis. So this is one of the invaders from which we have not secured our borders, Japanese honeysuckle, which has invaded decades ago and now has invaded forests throughout most of the lower 48 states. A recent study looked at the impact of invasive Japanese honeysuckle on risk of exposure to ehrlichiosis as a function of how it influences these Lone Star ticks. So this study took place in and around St. Louis, Missouri. This is a forest that's being invaded by honeysuckle, which dominates the understory. And what these researchers found was that, and what we're looking at here is the number of infected nymphal ticks per trap. That is a measure of our risk of exposure to ehrlichiosis. It was 20 times higher in parts of the forest that were dominated by honeysuckle as compared to parts of the forest that were dominated by native vegetation. Risk has gone up quite dramatically as a consequence of this invader. A similar study, a similar result has been found with black-legged ticks and Lyme disease risk as a function of invasion by Japanese barberry. This is an ornamental plant that gets placed in people's yards, and then it's hard to see here, but it also can dominate forest understories and create virtually a monoculture of barberry underneath the tree canopy. This is a recent study that took place in Connecticut demonstrating that here the density of infected black-legged ticks, and these are infected with the Lyme disease agent, is fully 9 times higher in parts of the forest that are dominated by a barberry understory as compared to areas that have no barberry at all. And if you go and mechanically remove barberry, and that's what's meant by controlling here, you can strongly reduce the abundance of infected ticks, but it's not as good as preventing barberry from invading in the first place. The second environmental change or disturbance that I want to talk about is that of biodiversity loss. And we know that we are now undergoing an unprecedented crisis with respect to biodiversity loss and extinctions. Species are being lost at a rate that exceeds even the pulses of extinction in the geologic past, including the extinction of the dinosaurs at the end of the Cretaceous. So this shows in recent years, this is between 1800 and 2010, the rate of biodiversity loss, the rate of extinctions throughout the planet. Research in my lab has demonstrated that biodiversity loss has a profound impact on our risk of exposure to Lyme disease. Lyme disease is one of the emerging infectious diseases. It was first identified, first detected in the mid-1970s and became a notifiable disease in 1982. And the number of cases of Lyme disease in the United States has grown inexorably throughout the past couple of decades to the point where Lyme is now, in some areas, the second or third most frequently reported of all the CDC's notifiable diseases. We know that particular different species within communities of mammal and bird hosts play distinctly different roles with respect to changing our risk of exposure to Lyme disease. We know there are some species, such as this white-footed mouse, that play a strongly amplifying role. More mice means more infected ticks, and hence higher risk of our exposure to this disease. And there are other species that serve strongly protective roles, reducing the number of infected ticks out in the environment. And what I want to show you is a little bit of data from our lab in demonstrating exactly how this works. This is a slide showing you the host permissiveness. This simply tells you the number of ticks that feed successfully on the average member of these different host species, where we place known numbers of ticks on these hosts in the lab and then follow the fate of those ticks over time, determining how many of them survive and become a potentially dangerous tick of the next stage, and how many of them get killed by the host during the course of grooming. And what we find is that about 50% of ticks that attempt a blood meal on a white-footed mouse are successful at doing so, and that's by far the most permissive host in this group. At the other extreme is the opossum, which kills about 96% of the ticks that attempt to feed on them. So these opossums, you may not believe it, but they are fastidious groomers. They end up protecting our health by hoovering up and killing vast quantities of ticks in the environment. We also know that these different hosts play vastly different roles in terms of infecting ticks with the Lyme disease pathogen. These ticks are not born infected. They have to get it from somewhere, and they get it during an early blood meal off some kind of vertebrate host. What we have determined in my lab is that 92% of the ticks that feed on a free-ranging, wild, white-footed mouse acquire an infection with the pathogen and become a dangerous tick capable of making you or me sick. There are several other species of small mammals like chipmunks and shrews that are fairly good reservoirs, infecting roughly half of the ticks that feed on them. But then there's a large group of larger mammals and birds like skunks, opossums, raccoons, and white-tailed deer that are extremely poor reservoirs and infect only a tiny fraction of those ticks that actually do survive the experience of trying to feed on them. So what we see is that biodiversity loss is in a very predictable pattern in the United States, and as is true elsewhere. The main factor that reduces vertebrate diversity, and this is true in the US as well as the rest of the world, is habitat destruction and fragmentation. And the predictable pattern is that when we go out and sample vertebrate diversity in large, extensive patches of habitat, we find a full complement of vertebrate hosts. So this includes the dangerous species that amplify risk and the protective ones that dampen risk to us. As we chop forest up into smaller and smaller bits, which we are very good at doing for a variety of reasons, developments of various kinds fragment the habitat, we tend to lose the protective hosts. The larger bodied hosts that occur at a higher trophic level are the ones that tend to reduce the number of infected ticks out in the environment. And what we end up with are the species that tend to amplify, these small rodents that are very fast-lived, and have apparently a very relaxed immune system, which makes them highly competent hosts for ticks and highly competent reservoirs for various pathogens, including that of Lyme disease. So we know, for instance, in Dutchess County, New York, that as forest fragments decline in size, down below about 2 or so hectares, we get this dramatic increase in the density of infected nymphs. Small forest patches are much riskier places to be than our somewhat larger forest fragments or intact forested ecosystems. We also know that some of these hosts play a particular role in regulating abundance of white-footed mice, this very important amplifying species. So a recent paper that came out a couple of months ago in PNAS demonstrated that foxes are one of these species that protect our health. Looking at the various sites in New York State over a couple of year period, these researchers found that the more foxes there are in a particular part of New York State, the lower the incidence of Lyme in the human population. In areas where foxes are declining or have disappeared, the per capita incidence is what is cut off from this axis. Per capita incidence of Lyme disease in that part of New York State goes dramatically up. When you look across time at a variety of different other states, what you find is over time, when foxes decline, that would be going from right to left, as foxes decline, the per capita incidence of Lyme disease goes up, and that has been found independently for Minnesota, Wisconsin, Pennsylvania, and Virginia. So foxes are serving a strongly protective role. They're one component of biodiversity that gets lost preferentially when we fragment and destroy forest habitat. So we also know that in this election year, Lyme disease has become a campaign issue. So this is a mailing that was recently sent out by the Romney campaign to all the residents of Virginia, and this right here says that the Romney-Ryan are doing more to fight the spread of Lyme disease. So I would argue, based on the data, that if Governor Romney really wants to be tough on Lyme, he should be tough on biodiversity loss and tough on invasive species in our forests. So the other example I want to give you for how biodiversity loss and change influences our risk of exposure to disease is that of West Nile virus. So West Nile virus is similar to Lyme. It's a vector-borne zoonotic disease. In this case, the vectors are mosquitoes, mostly in the genus Culex, also the genus Aedes. These mosquitoes acquire an infection with West Nile when they feed on an infected bird, such as this house finch. We're going the wrong way. And then they can transmit that infection onto us later in their lives when they bite the next host. West Nile virus invaded the United States in 1999 when it jumped the pond and was detected in and around New York City in 1999. And as this slide shows, it underwent explosive range expansion all the way across to the West Coast in a matter of about 3 or 4 or 5 years. For West Nile virus in North America, there are a number of studies that now have compared different birds, both songbirds and non-passerine birds, in terms of which are the most competent reservoirs, which are the most capable of passing on an infection to feeding mosquitoes. And the most competent reservoirs for West Nile in North America are the house sparrow, house finch, American robin, blue jay, American crow, and common grackle. Many other bird species have been tested, and they tend to be poor reservoirs for a variety of reasons. And you may notice something about this collection of birds. To me, these are, as a mammologist, these are nothing more than feathered white-footed mice. These are the birds that are highly resilient to habitat destruction and loss, to biodiversity loss. They are the kinds of bird species that thrive in suburbanized and urbanized environments. So we expected that there might be a role for avian diversity in the West Nile virus epidemic in North America. We hypothesized that low diversity communities, avian communities, would tend to become dominated by a few highly competent reservoir species. That would mean that mosquitoes would have high contact rates with these reservoir species, and we should see a high rate of acquisition of infection by these mosquitoes. That's what these red guys are supposed to be. We should see high infection prevalence in the mosquito population, and that directly increases risk of our exposure to this deadly disease. On the other hand, we postulated that high diversity communities should tend to contain a greater proportion of incompetent reservoir hosts. The mosquitoes bite these guys, but they don't get infected from them, and we thought that would deflect blood meals away from the most competent reservoirs, giving rise to a lower infection prevalence in the mosquito population and lower risk that you and I would get sick. So we tested this with essentially a nationwide analysis, a correlative analysis of West Nile virus as a function of bird diversity. So our prediction was that human incidence of West Nile should be lower in counties within the United States that have high bird diversity as a function of the Shannon Index, which is a generally used index of species diversity. Our data set consisted of 308, 813, and 30 counties that peaked in West Nile virus incidence, respectively, in 2002, 3, and 4, as it moved in a wave across the country. So essentially our approach was a nationwide regression of West Nile virus incidence, so this is per capita number of cases, and this comes from the CDC, against bird diversity, and these data come from the USGS via the breeding birds survey data. So what did we find? Well, we found strong support for the hypothesis that as bird diversity goes up, West Nile virus incidence goes down. So in each of the 3 years of the study, we found a highly significant negative correlation between bird diversity and West Nile virus incidence per capita in that county throughout the United States. And because these are plotted on a log scale, I want to emphasize that these were not modest effects, that if the difference in your probability of getting sick, whether you live in a very high diversity county, bird diversity, or a low diversity county, could be as big as a factor of 10 or even 50 in some of these years. So this was a dramatic protective effect of high bird diversity. Recently, we've reviewed the literature, the recent literature of study systems that have looked for a relationship between biodiversity and some measure of infectious disease, whether that is risk or incidence, transmission rates, or the like. And our paper published almost 2 years ago in Nature showed that, in fact, of 21 different systems in which this protective effect of diversity was tested, was examined, in 19 of those it was found. And in the 2 others it was not, but it was essentially no effect of diversity was found in those 2 other systems. And the number of different systems, the type of parasite, the type of host, whether it's vector-borne or not, whether it's aquatic or terrestrial, shows that this, what we call a dilution effect, is really quite general across a wide range of different systems. And the last environmental change that I want to talk about with respect to infectious disease is a more provisional one and controversial one, and that is how climate change is influencing or might be influencing West Nile virus in the United States. Biodiversity is not the only environmental impact on West Nile. Climate change appears to be having an impact as well. So this is a slide I don't think I need to show you, but I did want to show this morning over in the Rayburn office building that we know that the climate of the planet is increasing. We know it's increasing quite dramatically. It has been doing for a number of decades now, and we know that the major cause of that are emissions of greenhouse gases. And now there are accumulating pieces of evidence that support an impact of climate warming on various mosquito-borne diseases. So these are data on the extrinsic incubation period, on rates of infection of mosquitoes with West Nile virus. And what we're looking at here is we can compare, for instance, the number of mosquitoes that get infected at 25 degrees C, 28, and 30. So the number of mosquitoes that get infected, or the percent that get infected, is dramatically higher under warmer conditions, 30 degrees, than it is at 25 degrees. Of those mosquitoes that get infected, the dissemination rate, so this is the traveling of virus throughout the tissues of the mosquito, which is important for later transmission, is vastly higher at 30 degrees than it is at 25 degrees. And then the dissemination of West Nile virus throughout the population, again, is considerably higher at 30 degrees than at 28 or 25 degrees. Of those mosquitoes that do get infected, when it is warmer, the percent of those mosquitoes that actually transmit it to a host, such as you or me, is higher when conditions are warmer. So here we're looking at the days post-infection and the percent of mosquitoes that are transmitting. When it is cool over here, this is 14 degrees, these boxes. When it is cool, there is only very modest transmission, and any transmission at all requires more than a month to begin. Skipping over to these triangles, this is 22 degrees C. When it is warm, quite dramatic transmission can occur, but that starts to occur after about 2 weeks. And going over here to the left, these dots, this is 30 degrees. These are the hottest conditions. Quite dramatic transmission occurs, and it begins to occur after only a week. So it's much more rapid and much more greater magnitude when things are warmer. Well, the evidence also suggests, although these are preliminary, I consider the evidence preliminary, that drought also has an amplifying impact on West Nile virus. The main reason for this is that the main mosquitoes that transmit this pathogen tend to breed in containers of various kinds, in stagnant pools of water, such as in these storm drains. And this is some municipal workers in Dallas that are sending this robotic thing down into the storm drain system to spray larvicide and try to kill these larvae. These larvae occur in these stagnant waters so that when it is droughty out there in the real world, they tend not to get washed away. And the drought conditions lead to a concentration of nutrients, which gives rise to much more rapid development of these mosquitoes during the larval and pupal stages. So the evidence is reasonably strong for the West Nile system in North America that under hot, dry conditions, we see faster mosquito development, we have faster replication of the virus, they bite faster, which is very important in the rate at which they spread this disease, and there is some evidence that there's better breeding habitat when conditions are dry. So consequently, hot, dry climatic conditions should lead to greater risk of West Nile virus. Well, so far, as of the end of the summer, we know that 2012 is the hottest year on record in the lower 48 states. And I don't think it's a coincidence that so far, 2012 is the worst year yet for West Nile virus since it arrived in this country in 1999. We know there have been 4,249 cases and 168 deaths as of about a week ago. So I just want to close by saying that I've tried to provide a couple of examples of specific environmental changes and specific infectious disease health threats that are posed by those environmental changes. But I want to add in closing that these are only a few examples of what is undoubtedly going to be a worsening problem, that there are many, many different emerging infectious diseases. They are increasing in their discovery rates. And 335 different emerging infectious diseases of humans having been detected just since 1940. And I also want to point out that contrary to conventional wisdom, these are not things that go on off in the wilds of equatorial Africa or the Amazon basin. These are diseases that predominantly occur in the north temperate zone of both the western and eastern hemispheres. So what I think is important to take away from this is that these environmental impacts tend to exacerbate disease. We think we understand some of the underlying principles. These are likely to continue to be problems, and the science can really contribute, I think, to public policy that might do a better job of protecting our health. So I'm happy to answer questions. If there are questions.
Thank you for the excellent presentation. I have a question regarding your research on the protection from higher biodiversity and Lyme disease. Do you have any information regarding what effects non-native species, say feral cats or the expansion of coyotes, have in terms of the prevalence of Lyme disease?
Right, so the question is particular species, especially non-natives, what impact they may have on risk of Lyme disease, particularly feral cats and coyotes. Coyotes are native to North America, although they are expanding their ranges. Feral cats are not native to North America, although they've been here quite a long time. So there are data on coyotes, but very, very little on feral cats. But this is a great interest of mine because there are some of our small forest patches that don't fit the model, where they're very small forest patches. We expect elevated Lyme disease risk, but we don't find it. Those are almost always forest patches surrounded by backyards of homeowners who have cats that run free. So they're not feral cats, I don't think. They're owned cats, but they're going off and they appear to be scarfing up lots of white-footed mice and reducing risk. But we don't know in any systematic way what impact cats are having in the Lyme disease epidemic. With coyotes, the Levy et al. Paper that describes the impact of foxes in protecting our health, well, one of the things that is removing foxes, in addition to habitat fragmentation, is an expansion of coyotes. Coyotes are expanding because we don't have apex predators like wolves and mountain lions. Wolves and mountain lions are very good at preventing coyote encroachment, and so they are indirectly facilitating fox populations and protecting our health. So this is sort of a trophic cascade when it comes to carnivores and Lyme disease risk.
Nancy?
So I wonder, when you talk about these things, do you see any evidence that you're getting any traction in moving people toward thinking about land use, development, design decisions that would use these ecosystem services to limit disease risk, as opposed to spraying more larvicides, which seems so easy and seems to be the dominant trend for dealing with increasing disease risks, whereas pesticides are also risks.
Right, so the question is whether there's any traction in some of these studies in terms of feeding into policy, I guess, at the local or larger scales that might be useful for mitigating disease risk by managing biodiversity loss, et cetera, or managing invasive species. And the answer is that it's of interest. We know that there are international groups that have been following this line of research and are using it. For instance, with the United Nations Decade of Biodiversity, it's being used quite a bit with the new intergovernmental panel on biodiversity and ecosystem services. And I also know that at local levels, so where we've done much of this research within Dutchess County, New York, there's quite a bit of interest in local civic groups, local governmental groups at the planning board, zoning board kind of level. But I think that much, much more could be done to start to translate this research into actionable policy that could infuse environmental policy with health consequences. So this is in its initial stages, that environmental policy is tantamount to health policy when it comes to many of these infectious diseases. But that's a new idea. I hope it will continue to gain more traction.
Are you working with any invasive species issues that involve the direct impact of invasive species as reservoir hosts or vectors for diseases, rather than as sort of environmental enablers?
So the question is whether I am working with invasive species that have different roles rather than changing the environment in a way that influences infectious disease, invasive species that are either the culprits themselves. Is that fair? Okay. So, so I forgot to mention, well, I didn't forget. I did mention that West Nile virus is an invasive species. So it never occurred before 1999 in the Western Hemisphere. So in a sense, I'm working on that question. There are mosquitoes that have been invading all over the world that are capable of transmitting West Nile, dengue fever, and various other horrible diseases. And so they are spreading very rapidly. They get moved around with shipments of tires and other kinds of containers. So there is research being done, not by me personally, that looks at the impact of invasive species that are, in fact, either the vector or the pathogen responsible for the disease. And the take-home message is a very similar one. It's a like-minded one, that species invasions can compromise our health from a variety of different standpoints, not just the indirect effect of those invaders on the environment that indirectly amplifies risk, but they can also be the virus itself or the mosquito that transmits the virus.
Other questions?
Thanks very much.
So we're going to have one more talk, and then we'll take a short 5-minute break. And I say that mainly for the people on the end of the broadcast. But our next speaker is Dr. Paulo Dodorico from the University of Virginia. Paulo's presentation is entitled Societal Reliance on Global Freshwater Resources. Dr. Dodorico is the Ernest Earn Professor of Environmental Sciences at the University of Virginia. And his research focuses on the role of hydrologic processes in the functioning of terrestrial ecosystems, broadly defined. He's currently investigating the global patterns of virtual water trade and their impacts on water equity, social resiliency, and food security. Paulo? Which one's yours? It has your name on it. Why not?
Thank you very much for the introduction and also for the invitation. This has been a very exciting day, and it's really an honor to be here. So today I'm going to talk about, I kept the same title as this morning's title, but basically we're going to look at water in interaction with human societies. And we will first look at different forms of water consumption by humans, and then we will look at some relations between water, food, and population. And then we will look at how water is virtually transferred around the world in the form of virtual water trade. And then I will talk at the end about some alternatives that are recently appearing and becoming more and more predominant alternatives to trading virtual water in order for some societies to grant them access to water and to food. So first of all, most of the water we use as individuals is used to produce the food we eat. And drinking water is only a small fraction of our water consumption. So there is often a misconception that the water crisis is about lack of drinking water. Most of the times, the lack of drinking water is not due to, it's not an environmental problem. It's mostly due to lack of good governance or investment in water supply systems. Most of the water, if we look at now, at the water as a requirement for food production, we would expect that since water is required to produce food, somehow water should play also an important role in determining the rates of growth or the size of a certain population. If you look at different sectors of the economy, we see that industrial water uses are much smaller overall, and agriculture is really the big player. And most all food we eat comes directly or indirectly from agriculture. And again, here are just some more specific numbers. What is interesting to notice is also that there is some variability in household use of water. Overall, household usage is small, but there is variability which depends a lot on the type, on the whether the water is carried by people or comes through pipes into people's homes. Then if we look at the big player, which is again the water for food production, we see that there is a big variability depending on whether it's a more developed or a developing country. And this is mostly due to the fact that we tend to use food commodities that have different water costs for their production. And most notably, meat is a very expensive, water expensive type of food. It requires easily around 8 times more water per calorie than vegetable food. And it has been observed that as societies, during a pattern of development and of economical development, more wealthy societies tend to consume more meat. And this has been also documented by this study by the UK Government Office for Science. And they found that considering different countries like China, India, or even the United States, as the GNI, so the gross national income increases, there is an increase in the consumption of meat. And now we know that more meat means more water consumption too. So while we are talking, comparing different food commodities and looking at their water costs, we are implicitly looking at at the virtual water associated with the production of that food commodity. So we tend to define as water footprint of a commodity the water cost of that commodity, and then this concept of virtual water is really the virtual water of a commodity is really its water footprint. We can think that it's embodied in that commodity, even if it's not physically present in that. But then if we think in these terms, when we trade some of this commodity, virtually we are transferring this some water from a side of the planet to another. So there are areas of abundance of water where basically the local supply exceeds the demand, and there are areas in which the local supply cannot meet the demand. And then there have been other studies with other data sets, but basically overall we see that there are some regions of the world where the natural resources are not sufficient in terms of water resources to sustain their population. So when we look at, it's important at this point to look at a water balance and to compare the supply to the demand. We have seen that the population size and the type of diet affects the water demand. And we know also that climate and a suitable agricultural land affects the supply. So if the demand exceeds the supply, the society is in a condition of water deficit. And so it could go either through a pattern of malnourishment by accepting a consumption rate that is smaller than the demand, or import food from abroad. This requires that there is an area somewhere else where there is more water supply. The water supply exceeds the demand in a way that there can be a water surplus and also a surplus in the production of food that can be traded in the global market. So in this way, while we trade food, we also virtually trade water. And this led to this idea or awareness of the fact that there is a globalization of water resources, because virtually, as we trade these food commodities, we transfer water from a side of the planet to another. And this allows some societies to live in water-efficient regions. And a number of scientists tried to investigate this virtual network of water trade, because at this point, the virtual water trade constitutes a network in which each country, for example, is a node, and and each trade partnership represents a link. And so we can look at the properties of this network, and there have been some attempts also to model and try to explain these global patterns. And this is pretty recent research, and these authors found that some interesting results, that the degrees of each country, degrees is the number of trade partnerships with other countries around the world, is a function of the GDP, and which is a metric to measure the value of what is produced by a certain country, while the total amount of virtual water traded by that country is a function of the rainfall on agricultural area. There is we have our group has tried to study the how this network of virtual water trade has been changing over time. And so we have been looking at how quickly this globalization has happened. And to do this, we went to, we used the data from this data set of the FAO. And we used global trade data, and we were able to reconstruct, convert this into an analysis of the network of virtual water trade. And we found that these are just some of the major links. I think they are the links that carry 50%, at least 50% of the global trade. And we found that over time there has been an intensification in the number of links. But interestingly, only a few of these links were permanent, and so represent a very simple backbone structure of the network, and many of them have been intermittently activated or deactivated over time. The number of links, this would be the average number of links in each node, has been increasing over time, has almost doubled. And probably this gives a better idea what has been happening. Basically, the greener colors represent countries that have more trade partnerships with the rest of the world. And we see that overall the world has become greener, so there are more interconnections in this global network, except perhaps for except for Africa, that remains pretty much marginalized and excluded by this global network of trade. Then it's interesting to look also at the growth in the total volume of trade, mostly contributed by plant products, but also by animal food products. And then here it's interesting to see how some of the luxury products, which could include like chocolate, coffee, or alcohol, these are also part of this, are also traded in the global market. And so this increase in trade, and this goes back to the first talk of this afternoon, this we show that there is an increase in the volume of virtual water traded, even if we look at normalized by the number of people. So this is not just a trivial effect of the increase of the world's population. There is much more to it. Perhaps it's related to the also to this change in diet I've been talking about. Then if we look at the net exporters and net importers over time, there has been we observed that there have been less net exporters, and this is interesting because it tells us that the number of countries that contribute, and this will be the next slide, to the global, to the net exports of virtual water has been decreasing over time. So there is more and more a concentration of basically the contributors become less, and so the control, I would say, on the global network of trade remains with less countries. The big change here is the US remains about the same between, these are, I took data from the 1986 and 2008, but the interesting thing is that we observed is there is an increase in the contribution of Brazil to the global trade of virtual water. So what are the general properties? Most of the flow in this virtual water network concentrates in only in a few links and nodes. So there are many trade partnerships, but just a few of them carry a lot of flow. In fact, many other countries remain only marginally connected to the network. Then 50% of the fluxes are carried by 1.1% of the links. And then the major contributors that the countries that contribute to 50% of the global virtual water that is traded in the global market are just 4 or 5 countries, and and basically these 50% of the flows are controlled by 6 or 8% of the global population. Then in this period of study, we found that an increased importance of Argentina, Brazil, China, and Indonesia in the global trade of market. China is one of the major importer of virtual water from the rest of the world. The effect of virtual water trade is to allow some countries that in which the local supply would not be sufficient to meet the demand. The virtual water trade allows these countries to meet, which would be the green countries, to meet their demand. In some other countries go very close to that. But again, is virtual water a virtue? For sure, there is the virtue of allowing some regions of the world not to suffer an intense effects of water stress, which would be malnourishment and famine. At the same time, there are some negative aspects that I try to summarize here. One of them is the disconnection between the centers of production and centers of trade. The fact that consumers are far away from the agricultural land that is used for the production of food makes them less responsible for the environment. In particular, for the environment from which they draw their resources. And so this leads to, in my view, to a loss of environmental stewardship, this behavior that should make us responsible for the environment we live in. At the same time, there is virtual water trade that does not enhance the equality in the access to freshwater resources. So there is a basic inequality that is dictated by geographic and environmental constraints, but virtual water trade doesn't try to fix that, but in fact it works in the opposite direction. It even increases inequality, just slightly, but it does. And then in the long term, it's not a solution to the water crisis. At some point, we will see that more and more water is used and appropriated by the humanity, and at some point the system will reach its carrying capacity. Finally, I will try to show that there is an effect of loss of societal resilience. First of all, to evaluate this effect of loss of environmental stewardship, we can look at the environmental cost of food production, mainly of agriculture. We know that agriculture has some costs, environmental costs associated with pollution, and this can be quantified by looking at the amount of water that is necessary to dilute these pollutants and bring them below the water quality standards. So for each food commodity, we can associate with that a so-called gray water footprint, which means really the amount of water that for a pound of beef, for example, we need to place back, we need to have available in the environment in order to operate an environmental, to dilute these pollutants and bring them within acceptable levels. In the case of the US, we see that this would be the the grey water cost of export to from the US to these countries. And then if we look at the global trade, we see that the burden of food trade measured by this grey water footprint is much stronger in the US and in many other countries. So this is just, we propose this as a method to evaluate really the environmental cost of virtual water trade, costs that are seldom or are never accounted for when we buy things in the supermarket. Then to evaluate the inequality, we did this type of analysis. We we used some of the metrics that economists developed. And basically, if a certain percentage of the human population was using a certain proportion of the water resources, the same proportion of water resources, for example, 80% of the people using 80% of the resources, there would be no inequality. Instead, the problem would be if 20% of people have control of over 80% of the resources. So we can try to plot the real data along this diagram. And what we observe is that in many cases, the data points would fall on a line like this one. Then by taking the area that is between the one-to-one line and the data points, we have, multiplying this by 2, we have the so-called Gini coefficient. So if the Gini coefficient is 0, this means that there is no inequality, because basically all points would fall on the one-to-one line. Instead, if the Gini coefficient is larger than 0, there is some inequality. So we have done this for both for agriculture and industrial products. Let's focus on agricultural. For example, you see that the line is way far from the one-to-one line. And then we can also look at the different contributions of industrial, internal agriculture in each country, and industrial activities, etc., and their total contribution to this global inequality in the use of water resources. And we see that most of the inequality is contributed by the local agriculture. Overall, virtual water trade plays a small role. This would be the external part of the footprint of each country. And we see that, but still it increases the inequality in the system. So this brings us to one of, I would define this one some sort of ethics, water ethics dilemma. Is the unequal distribution of freshwater resources unjust or unfortunate? Because most of it seems to be controlled by a geographic distribution of the natural resources. And it's when we look at this ethics problems in the time domain, we tend to compare this generation to the next. And then we would expect that this generation should the next generation should have the same access to the same amount of resources. In the space domain, things are completely different. So, I think there is the need to understand or to come up with some criteria, or we can just wonder if really what constitutes a form of injustice in what is just the result of this geographic distribution of natural resources. Let's go to the third point, demographic growth. So we already went through this and we looked at that curve several times. The way I look at this is that there has been an increase, a dramatic increase in population in the course throughout the history of the humanity, but particularly in this century. For the last few decades, there has been an increase of the population by 1 billion almost every 12, 14 years. The way I look at this is that there has been a big jump here, and this coincides more or less with the development of fertilizers. Then at some point, probably there was the idea that the humanity would have had unlimited access to food, but at the same time we are limited by other factors, and one of them is water. And so at some point, some scientists have been asking the question whether we will run out of water by the year 2050, 2100, etc. The basic idea is that if the population grows but the water resources remain the same, at some point we should reach that limit. And I would define this one as this period of time as the virtual water era, a period in which we have the luxury of dealing with the regional water crisis by transferring water resources across the planet. But again, at some point we will reach this limit. So then the other thing that is interesting to see is that if we look at what's rich countries, we can define them as countries where the local supply exceeds the demand. Trade-dependent countries are countries in which the demand can be met only by bringing water through virtual water trade. Ecologists have been modeling population dynamics most of the times with a logistic equation, where this term here is the carrying capacity, and in our case is somehow related to the water availability. So we can define a local carrying capacity based on the local resources, and a virtual carrying capacity, which is the local resources plus and minus what is associated with the trade. And then we can look at the population data and plot this population and plot the logistic growth using this population data. The interesting thing is that we are not fitting parameters because we are not fitting this parameter because this parameter comes from a water balance type of analysis. What we find is that the water poor countries tend to have a growth that is controlled by the virtual water capacity, while the water-rich countries tend to follow a pattern that is controlled by the local resources. So what I'm trying to say is that here we will reach soon a situation in which this imbalance in the use of water resources will become obvious, because demographic growth of exporters does not account for the fact that they are currently giving this virtual water to other countries, while importers already rely on these imports. The third point I would like to the last point I would like to show here is the issue of societal resilience. So until recently, human societies tended to use resources locally. And population growth was constrained only by the, as we have seen in that simplified model, on the locally available water resources. And in case of crop failure, there would have been just a local effect and, of course, some sort of water stress. Now, in a global world, there is the virtual water is traded, and there is population growth has no more been limited by the global, by the local resources, because of this access to other resources through patterns of trade. And what happens in case of a drought? Well, it depends on how much other countries, in case of a drought, can supply water to, and food to another part of the world. And again, we are probably in an intermediate, as we have seen, in an intermediate situation in which there are a part of the world that is very well connected, and still some communities or some societies that are pretty isolated because they don't have access to this global market because of their development status. And thanks to virtual water trade, we have that less of unused water resources that are in water-rich countries that would not be used by these countries, are sent to water-limited countries in a way that we can sustain a bigger global population. This means that there is a decrease in redundancy in this system. And in a case of drought, there are less resources around the world that could be available to meet the needs of the society or the country that is in condition of drought. The way I'm heading is I'm going to look at something that in ecology is called the insurance hypothesis. Basically, the idea is that less redundancy coincides with less resilience, because if any system has some redundancy, can absorb better the shocks coming from an external disturbance. But if virtual water trade is causing this, the fact that less resources remain unused, the system is less resilient and is less redundant, and therefore less resilience. We tried to show this again with a simplified model, and is strongly inspired by this idea that optimization in a sense use most of the existing resources, and resilience don't work very well together. And with this simple model, I'm not going to go into the details, but basically we consider three different scenarios: a world of local water use, a world of global water use, and a world in which we have this idea of water solidarity. In this case of water solidarity, we allow the connections and trade to happen only in conditions of crisis, and so only for the duration of the crisis. With respect to the globalized world, we don't allow, and this is just a sort of a game, but we don't allow the demographic growth to occur in a certain community, relying on transfer of virtual water from other communities. What we find is that while in the globalized world, there is a much higher susceptibility to drought-induced mortality in the case of a big shock. In the case of water solidarity, as we increase the connectivity of the system, we have a decrease in the susceptibility to this drought-induced mortality. So in a local water, this tells us that there is a way to use the connectivity of the system through virtual water trade to our advantage to improve the resilience of the societal resilience. Alternative to trade, I will mention this briefly. I said before that one way for a water deficit country is to rely on virtual water trade. An alternative could be, and we observe it is through land and water grabbing. So this is something that we became aware and in recent years, particularly as a result of changes in US policies on biofuels and also in the in the European Union, etc. There has been more the world has become aware of the fact that land and investment in agricultural land can be become crucial and could be important both for corporations and for foreign countries. Land grabbing is a form of transnational land acquisition that occurs usually with no transparency, without really consent of the land users, and without looking at the environmental societal impact. Land grabbing is not only a rush for land, but is also for the water resources that are associated with that land. Otherwise, nobody would go and get would not invest in that agricultural land. So we have done an assessment of this phenomenon. It affects almost all continents, with the large grabbing from and with these arrows we show that this country is grabbing this other country, etc. And even here we have a network. Even here we have a virtual transfer of water resources. So we have tried to quantify this. And first of all, just to show the final results, the most grabbed country is Africa. I should have shown a similar picture also for the grabber who is grabbing these countries. And if we look at the amount of water resources that are grabbed, this is not overall not a trivial amount. I probably didn't stress the fact that when I was showing the global trade, we were in the order of 10 to the 12 cubic meters globally. This is there are some ones in front of this. This is like of the order of 10 to the 11. So there is a substantial amount of water that is grabbed around the world. Here I'm sure in this community we tend to call green water grabbed as the for rain-fed agriculture, while irrigated the blue water would be water that is supplied as through agriculture. So there is a significant, substantial transfer, a virtual transfer of water, even through this mechanism of grabbing. And then if we look at some of these countries, again, there are some ones in front of these even twos in front of these numbers, which means that since 1,200, 1,300 is the per capita water requirements for a balanced diet, if we show this data as a per capita in the grabbed country, we see that the water resources that are taken away from these countries would be sufficient to eliminate malnourishment and to provide food for the local population. And just some quick conclusions. I hope I'm not running out of time. Some countries are in conditions of chronic water deficit, and this is possible because of this virtual transfer through virtual water trade. And more recently, some countries and corporations are trying to have access to water resources in other countries, not through trade, but by going there and buying the land. And with the local water use, we have a tighter relationship between producers and consumers. This allows for the development of a relationship between humans and environment inspired by the principles of ecosystem stewardship. Gives a overall stronger sustainability, and overall the resilience to drought is pretty small, because we cannot benefit from this transfer of water resources from other parts of the world. So one of the merits of virtual water trade that is leading to the globalization of water resources is really that it allows us to face conditions of stress by importing food. And this is for sure one of the major benefits, and was often acclaimed also as one of the remedies to avoid water wars. At the same time, there are some negative aspects, and because associated with the fact that we maximize the use of the water resources, and we can sustain a larger global population, but this reduces the global resilience with respect to the other disturbances. And then we have the problem of this disconnection between consumers and producers in a way that there isn't much hope to have any effective environmental stewardship. This other model I was proposing is instead some sort of based on this eat locally and think globally. So if in an ideal world everybody would rely on the resources that are available locally, and they would even control its demographic growth accordingly. And just in cases of really extreme events, we could activate some long distance trade of food commodities and of virtual water with that to face the conditions of crisis. And with this, I'm ready for some questions. Yes?
So I'm interested in the role of technology. Having lived in Senegal, I know that they have no deep borehole wells which supply regional like cities. They have very few irrigation systems that work. They have, and that's not because of the resources, not because of the physical resources, because of the infrastructure. The technology is either has never been put in, or if it's put in, it breaks down in a couple of years. So some of the analysis you use, sort of, how do you put that into the equation? Because not only are there no little technology, there's also very little information about how much underground water there is, how much, what is the possibilities, since there's very little infrastructure, since there's very little industry. So it's sort of a tight spiral.
Yeah, that's a great question.
Could you repeat the question?
Yeah, the question was about the role of technology, and of course technology could play a very important role, and so how we could account for the effect of technology in all of this. That's a great point. I haven't included here any form of economical consideration on what type of investments or what type of governance would be required to enhance technology and use technology to increase our not only access to water resources, but make a better use of them. For sure, this is what we observe all the time, and that good technology, in particular in terms of irrigation, could greatly increase the agricultural production. For sure, there is also a lot of bad technology, in particular in countries that are in very arid environments. The example of wells has been often there in many places the development of wells has brought to the catastrophic consequences of overgrazing that without the wells would not be. So it depends on the type of technology, but good technology could really allow us to expand the, if we can say, the carrying capacity of each country, definitely. Yes? I think it's mainly, and again, there was, the question was how come that the US has a much bigger gray water footprint associated with its trade, while Brazil, which is also a big exporter of this comparable magnitude, has a much smaller gray water footprint. And the answer I have, and these are recent numbers, so I need to check where they are coming, what is behind that. But most likely it's the different use of fertilizers and pesticides in the two different countries. There might be, yeah, that's something that needs to be verified. Yeah.
Any other questions? Yes.
I was wondering how property rights fit into the virtual water trade in terms of exporters and importers. Are there different types of property rights? Is the virtual water trade changing from, say, open access to privatized, or vice versa? How is that?
Well, the way the virtual water trade is calculated is by taking directly data of international trade of commodities, and then through life cycle analysis for each commodity, you can determine the virtual water or the water footprint of that commodity. So it's done with some sort of a bottom-up approach, starting from the commodity without looking at where at the impact of the property rights. The question was, I forgot to summarize this, was about how property rights could affect or should be accounted for in the evaluation of virtual water trade. And so I think there is a layer in the middle which is not accounted for. I haven't looked into that because we use directly trade data, but is how property rights affect agricultural production and whether they affect, and also whether they affect the range at which these products are then traded and transported. Yeah. Thank you.
So at this point in time, we're going to applaud Paulo. Okay. At this point in time, what I'd like to do is just take a short 5-minute break. It allows you to get up and get your blood circulating. We'll come back. We have 2 more talks before the symposium is over. So those in the room, if you could be back here in about 5 minutes, and those online, we'll begin again in 5 minutes. I'd like to go ahead and get started, so if you all can migrate in and have a seat, there'll be plenty of time to chat at the reception afterwards. Hey guys, sit down. So welcome back, and we'll begin the second portion of our symposium with a presentation by Dr. Molly Brown. Her presentation is entitled The Role of Ecosystem Science in Food Security Assessment. Dr. Brown's day job is as a research scientist in the Biospheric Sciences Laboratory at NASA Goddard Space Flight Center, and she's graciously taken the day off to speak with us today. Thank you for that, Molly. Current research interests are the impacts of climate change on urban areas, understanding the effect of environmental variability on food prices and market functioning in Africa, and the use of remote sensing to better estimate mitigation and adaptive measures in these areas that are affected. So with that, I'll turn it over to Dr. Brown.
Thank you very much. So today I'm going to talk about how environmental change and ecosystem functioning affects food security. And the context will be the global food system and how the US government looks at food security and food security crises. I'll talk a little bit about the link between agriculture and weather and how weather affects agricultural production, and then how commodity markets affect ability of people to eat, food prices, and food access, and then I'll have a few summary slides. The collaborators, this is just like many scientific endeavors, is a group project. I have a lot of collaborators. I have Chris Funk and Jim Verdon who work with me on FuseNet, as well as Gary Eilertz and Fabian Tundell who helped with the economics. Kurt Reynolds provided some of the slides, and Tim and Ken from University of Maryland, Kirsten DeBurs, Burun, Compton Tucker, et cetera. So the foundation of this work is that the environment really matters. It matters because the global food system is changing, and we really need to, as we've been talking about all morning, all afternoon, is about how global environmental change affects agriculture and agricultural change. So there's been much stronger links between food prices and fuel prices. And this really began in 2007, 2008, when the US government changed its policies to augment biofuels. And what happened was we started using corn and other agricultural products to create ethanol, and ethanol became mandated as 10% of our gasoline in the US. And this has really strongly linked, for the first time, really, variations in agricultural prices of corn and wheat and soybeans with petroleum prices. And then another factor that's happened is an increasing use of commodities in investment portfolios after 2008 and the crash that's happened. We need to find somewhere that's safe, and so commodity prices are far more volatile, and there's money to be made. And while all of this is going on, we also have climate variability, which tends to reduce predictability and increase the likelihood of extreme events. And then the need for information about who's having a drought, what impact this drought will have on global agriculture increases, which is why I work on these issues, because satellite data, and NASA is a premier, globally, is one of the premier agencies that produce new satellite data records and monitors and manages earth science data, and understanding how satellite data can be used to understand agriculture and agricultural variability, and in conjunction with understanding of prices, we can look at how extreme events might have a negative impact on food security outcomes. So food security analysis is very broad, and needless to say, food security has nothing to do with the environment. It is an economic, a cultural, political outcome. We have in many, many different causes. And so there's really, it's extremely multidisciplinary and difficult. It's very complex. And so the U.S. government, through the U.S. Agency for International Development, funds the Famine Early Warning System Network, which warns decision makers of usually very slow fuse events. It's never a surprise. It's not like all of a sudden, overnight. It's not like an earthquake, which happens suddenly without warning. Food security crises are very long in the making. Usually it's decades of reducing effectiveness of local governance and increasing drought and reducing effectiveness of agriculture, and things spiral out of control, and then a shock occurs, and then a crisis happens. And then it takes a very long time to respond. It can take 6 to 9 months to bring in aid, to organize response. And so the whole thing happens in slow motion. And because of that, lots of quantitative analysis can happen, and Earth information systems, particularly on what's happening on ecosystems, becomes very important. So food security, I needed to tell you all a little bit about this because it's a diverse audience. I don't know whoops, excuse me, wrong button, pardon me. So food security analysis is a part of, it's basically the ability of all people to attain sufficient food for an active and healthy life. That's the official definition. There are 3 aspects: utilization, availability, and access. So with utilization, it's usually, that whole utilization area is in the health domain. It is really it's about an individual, whether or not you're well enough to use the food you eat. And so that's really in the health domain. And availability is where we can use satellite data. We can figure out, was enough food produced in this region or country for the people who live there to eat? And then access. Access has to do with prices. It has to do with equity and livelihood. How do you make a living? If you're a farmer and you eat the food you grow and you have a deficit, then not only do you have to make up the income you lost, but you have to actually spend more money to replace that food that you're not eating. So it's sort of a double whammy, right? If you are a wage laborer who works on a farm and there's a big drought, you lose your source of income and you also have a problem. But if you work in a factory, like we had a drought in Virginia in 2007, no one was hungry, right? Because the farmers may have a reduction in income, but they had a safety program, and so they had drought insurance, and nobody was hungry because very few people, only 1 or 2% of Virginian residents, are farmers. And so therefore, this is, this is very important to understand the complexity of food security in all the different aspects. The Famine Early Warning System Network has 23 countries in which it has offices with food security analysts, and it provides information over a very broad area of the world, mostly in West Africa, Central America, and Afghanistan. And they have a process where they use physical science data from satellites, from local networks, in conjunction with socioeconomic data on food prices, production, livestock health, whether or not kids are going to school, what's the economic situation, really broad amount of information brought together in an analysis, which is usually done in the country by local people who know the area, so it's not done in Washington. And then these reports go to come to Washington, D.C., provide analysis briefings, which is done in the context of broader State Department and federal government response, along with usually with the Food and World Food Program and international actors. And the whole objective of the process is to influence annual budget cycles. This, so it might be that Venezuela is saying, we're having a crisis, we need food aid, and in fact, it isn't really such a big deal, and they really don't need aid, but it's politically expedient for them to ask for it. And other countries who are having a crisis are not asking for it. And so a lot of what FuseNet does is sort out all of those aspects and make sure that the outcomes are the focus and not the politics. So how is earth science data used in all of this? As a person who's worked on satellite remote sensing, I personally find FuseNet and food security fascinating, because you would think that remote sensing has absolutely nothing to do whatsoever with economic. I mean, it's purely an economic thing. If you have this budget and you have this much deficit, and why is it that remote sensing is even relevant at all? And so that is really the question. How is it used, and why? What is the role of remote sensing within the FuseNet organization? And one of the things that it does is it's an objective analysis of hazards. If you can imagine the gray plane of politics, everybody has a competing cause, and everybody is talking about their own thing, and nobody can figure out anything. It's really those remote sensing-based maps, and I'll show you a few in a minute, that get people's attention. Everyone can come around it. If you have a rainfall, deficit or a severe drought, it is extremely easy to show a map and say, this is why we need aid now, and everyone can get behind it. If it's a complex cause by, a cholera outbreak, and it requires 4 paragraphs of explanation, not so much. A lot more difficult to get assistance, a lot more difficult to get the message across to all the complex actors that have to happen, because food security response is a complex, consensus building decision, like many things in international government. I know you all know what I'm talking about. So, and not only does it provide quantitative identification of potential changes in agricultural production and the value of assets, but it also provides the earliest source of information and is the least controversial. So here's a map. This is an animation of what remote sensing can see: rainfall, clouds, humidity, soil moisture, floods. And the information comes from a very wide variety of Earth-observing constellations. NASA has, has many terabytes of data coming out of the sky every single day. My favorites are Aqua and Terra, which give you information about the atmosphere and the vegetation conditions, but there's a lot of new ones. So here's the soil moisture animation. This is from a model, but the reason why I like this animation is because it shows you a parameter which will become which will be based in observation territory once the soil moisture active-passive mission is launched, which will happen in 2014. Let me run that one again. So it's really cool. You can see the red places have very low soil moisture, and the blue places have very high soil moisture, and you can see the monsoon going up and down. So this data will really, for the first time, allow us, instead of using rainfall data, look at the soil moisture productivity directly. Vegetation index is another parameter where we look at the health of plants directly. Instead of trying to figure out what's underneath the plants, we can look at the plants directly. There's data from 1981 for the AVHRR series, or in 2000 for the MODIS series, and let's look at that one again because it's so much fun. And here you can see the white, which is the snowfall, and the greening up and the browning down. So it's really visceral. So this is the kind of information we use to understand, to detect anomalies and to identify problems. So one of the things we can use this information for is, let's see if it will go, is to look at production. So here's wheat. This is a relationship. I'm showing you now anomalies of vegetation index in Australia in 2002, and the red means it's very dry. And in 2002, they made 10 million tons of wheat. And then in 2005, if you see, it's going to be very green. And when it's very green, you have much bigger production. See how green it is? And they made 25 million tons of wheat. And in 2006, you see how red. You guys, you have one guess about how many millions of tons of wheat was produced? 10 million tons. So it's really, so this is what we call linear models between yield and vegetation index anomaly. So it's really straightforward if you have information on the ground about yield. Unfortunately, we do not have yield information in most of the countries that have food security problems. We have beautiful yield information in countries that are developed and have developed agricultural systems, the US, the European Union, Australia, Russia, not so much, Brazil, getting better, but all of Africa, the yield information is very much missing. And so what we do is we develop models in places like Australia or the United States for corn, and we apply them. We take the NDVI anomalies in Africa, and we apply them, and we say, looks like it's going to be a below average, and it might be 20% below because of my nice guess. And that is how we go forward in FuseNet. So how else, other than that, how do we make these data products more useful? We need to integrate them with economics to understand risk, estimate the impact within a structure, to allow linking of causes to consequences, and we need to show how trends happen. So this year, this is the global wheat, soybeans, and corn. This is the global production from 1964 on the left, right up to 2011. And you can see that area has gone up only slightly, but yields have gone up enormously for all three of these crops. If you look at the United States in corn, wheat, and soybeans have gone up a little bit since 1946, but it's really corn which has gone through the roof. I mean, the transformation of the corn agroecosystem has been fantastic. And this is really where yield and technology has made such a gigantic difference in the United States. If you look at the differences in yields between the United States, the EU, the Soviet Union, South America, and then sub-Saharan Africa way down at the bottom, you see that Africa has really been left out. We've managed to transform our agroecosystems, right, using this technology through enormous applications of fertilizer and pesticide, yes, but mostly it's in genetic modification, changing of the seed stock, having this huge industrial system where we have companies that invest in technology and then they sell to there's 200,000 farmers in the United States where there's 200 million farmers outside the United States. It's a huge thing. How do you inform 200 million people that, the new system to, so the green revolution is very, very complicated, right? And so, but this is really the cost, the fact that the yields have not really gone up. How Africa has met its demand is through expanding area, not through expanding yields. So in the United States, we had a drought, and I showed this morning a picture of the drought. It was extremely severe, and you see this is the average from 1982 through 2013 or 2012, and you can see that the 2012 drought was the largest in the past, since past 3 decades, basically. The last time we had such a big drought was in 1989, where we lost 72 million tons of corn. This year, it's 103. So it's really record shortfall. However, if that same drought had occurred in Africa, they would have produced absolutely nothing, because the yield varieties they have now really provide a lot of protection in corn in particular. Doesn't do a lot in other areas, but corn is really buffered from these yields. So instead of losing 100% of their crop, like would have happened in cornfields in Nigeria, it was nearly 70% of what they expected, right? So this is a success, right? So it's really quite an accomplishment. And as I said this morning, the 103 million tons that reduction in the United States was, it's basically almost all of the global reduction in yields in production this year. There was 841 million tons of corn grown in 2012, this summer season in the world. So you can see that although there was droughts in Europe, it was not really very important in overall numbers. If we go back to and look at where the people are hungry, all the hungry people are in Africa. And if you remember back here, it's pretty average year this year in corn. There are droughts happening in other places in Africa this year, but they are not corn. They're not droughts in corn because most people, like in West Africa, eat millet and sorghum. Corn is not a huge crop in West Africa, for example. So these extreme, particularly in the Sahel, their problems are a little bit having to do with droughts, but most of it is the coup in Mali and geopolitics and extremely high food prices. So these are non-environmentally related food problems. So going back to I have to show my sort of larger structure here. What's really important is that agricultural production is influenced by many things outside of rainfall, things that we can see with remote sensing. We can see rainfall and temperatures, yes, but really, and we can also see, area and cultivation and change, but really what affects agricultural production is a growing population, that huge increase in population that we saw earlier, falling poverty and rising diet expectations, everyone wanting to eat eggs and bacon for breakfast instead of millet gruel. I mean, yes, me too, right? So if we had this enormous expansion of the middle class means that everyone, the demand for eggs and bacon in the world, I'm sure you all heard about the bacon crisis, right? So this is really has a huge impact on market forces. The fact that we use corn in our gas tanks means that more corn than ever has been put into cultivation, and that has an ecological cost, but it also provides resources for, the fact that we can grow all that corn, but we don't actually consume it is quite incredible. So, and then technology. I think technology is really where the big difference between what happens in the United States and other places and how we can address food security in the future will be through technology. So as we go forward, world food demand could double in the first half of the 21st century. The World Bank estimates that the number of people with rising, so this is but rising diet expectations. Yes, it's great. Getting people out of poverty is critical, but we can't all eat eggs and bacon in our current food system. And how many low-income consumers escape from poverty is the most important determinant of global demand. And because we have 7 billion people, we can't all live like Americans, right? So, yield growth is projected to decline, but this is both a problem and an opportunity. As I said this morning, these areas here, the United States and China have extremely high yields. This is sort of these are statistics when you put wheat, corn, soybeans, rice, all in the same bucket, and you sort of stir, so it's the total yields. Remember I said before, these statistics are not very certain, but we do know that in West Africa, it's 1,000 kilograms per hectare, whereas in China, it's 7,000 or more, 8,000 kilograms per hectare, and in Iowa, it's like 10 kilograms per hectare, right? But if you put all of the entire U.S. agricultural system, it's 7, right? So, so this means that this is a huge opportunity. The breadbasket of the future are in these places that don't use any technology. Most farmers in Africa don't use any fertilizer at all, none. So they use only cow dung. For the cow dung, they don't burn, right? So if we can look at this as an opportunity, these places here, Sudan has a fantastic rich soil, could be the breadbasket of West Africa. It could feed almost all of Ethiopia if it could get its political act together, get roads, economic development, and use some fertilizer and improve technology, gets access to some of these seeds. So there's much that can be done, and the fact that the demand for food and the fact that food prices are high is both a risk and an opportunity as we go forward. Again, poverty is the root of household food insecurity. It is not rainfall or temperature. It is geopolitics and poverty. high food prices are bad, but they're also good. So I'm trying to, it's a complex story, but in general, when you live on very little money and food prices go up, you're having a lot of trouble. Hunger is due to poverty, except in times of war. And then the higher food prices increase the incidence of hunger, and prices are really higher. So I wanted to show you all the increases in producer prices in the United States. Today, soybeans are $17.89 a bushel, which is, look at that curve. That is wicked, right? This is why Brazil, rapidly transforming its Cerrado into soybean fields. Wouldn't you? If you had, one of these days we will all be putting our backyards into soybean and corn. It's incredible. And here, the corn prices, this is before the drought happened. So they're now way up here, right? So it's the prices for corn and soybeans are going through the roof. And if you look at the food price indices, which are standardized to assess how much food costs if you were a country buying food on the open market, you see also a very large increase in 2011 and 12, which is equally high as 2007 and 8 after. So you had a big transformation here when in 2008 when we had that biofuels. But this increase in prices in 2007-8 and today is not due to production declines. We are at historic highs for production. So it's entirely economic. It's entirely food system. It is not due to production problems. So you should think, well, when we have this huge production decline to this year, what impact will that have on food prices? They're likely to go up even more. So it's really, the economists that I've read all the papers this summer. I've been reading all these economic papers, and the enormous amount of diversity of causes and what's going to happen. It's really, the commodity markets have become unhinged. It's very hard. Where is their base? If we are now connected with petroleum markets, what makes the price of oil go up and down? If you could tell me that, you'd be, if we really knew, we could make a lot of money on futures, right? So there's a lot of uncertainty in this, and I think that the climate change and the food, the droughts and the all of this environmental things have not yet hit. This is not caused by environment issues. It's caused by a transforming economic markets, right? So the next part of this is going to be talking about how do these high prices affect local prices. So I wrote this paper, which came out in the summer, called, which looked at how global prices affect local prices, and we looked at the regions where fused networks in these 5 areas: West and East Africa, Southern Africa, Central Asia, which is just this little part of Central Asia, and Central America. And note that South Africa is excluded from the analysis. So if you're a South African specialist, you can ignore everything I'm saying about Southern Africa. So and basically what we did is we looked at the FAO cereals index, which is basically wheat, rice, and corn at international ports and at capital markets, city markets. And we created regional and country level indices, both of wheat, rice, and corn, but then of the non-cereals. And for me, the non-cereals are most important because those are the cereals that people really eat. Beans and potatoes, sorghum and millet, cowpeas, cassava, and yams. This is what the poorest people in the world eat and that are most relevant to food security. So when you make these indices, you get this. It's very nice, essentially, and it's very hard to see, but essentially you can see that, for example, here in East Africa, this is the FAO index, and you see the local prices when you calculate a price indices just using East African data, no international data, East African data, you can see that the prices follow along and respond to the international peak. Other areas, not so much. So when you do a Granger causality, when you do an analysis that says, are the global international prices of cereals driving the local prices? What you see is that East Africa, Central America, and Central Asia their prices are determined by the international price. But in Southern Africa and West Africa, their prices are not determined by the international price. And in West Africa in particular, they are extremely unconnected to the international price, which means that they eat food that is grown locally and not food from Iowa or Kansas or from Brazil. They just can't afford it. They don't import it. They're isolated. They just do not have the connection. And so here is, so for example, Central Asia, here is the Central Asia prices. Actually, I'm not quite sure. Oh, here, okay, here's West Africa. The figures are a little bit messed up because of this PC Mac thing. So here in West Africa, you can see that you have a peak here, a response to the international prices, and that West Africa is not integrated into the international market. And if you look at the country level, you can see that the integrated places tend to be pretty, like Nigeria, for example, has a huge amount of petroleum resources. They have a lot of international trade. They buy a lot of grain on the open market. Ethiopia, Afghanistan and Tajikistan, El Salvador, Honduras, Haiti, they're all integrated. A lot of other countries are not. And so for me, what this tells me is that my remote sensing observations in places that are not integrated are far more important. When you are seeing a big drought in Mali, you should pay attention because they are eating the food they produce. 85% of the people in Mali are farmers. When they don't produce enough, not only do they have to replace their own food, but they simply don't, they have a consumption, they just are unable to meet their needs, and you see an increase in food insecurity. At the country level, we have a much greater, you can see a big diversity. In Niger, you see a non-integration, but if you use the remote sensing information, the NDVI, in the analysis, you can increase the connection between the global and the local prices. Here you see the correlation goes up from an extremely low 0.5 between the local prices and the global prices to 0.37 if you use the NDVI, which means you get a lot of information out of the local environmental dynamics. In Kenya and Uganda, Kenya you see a little bit of an improvement, and Uganda not at all, even though it's not very integrated into the global economy. And Haiti and Afghanistan, there's absolutely no effect, which means if you're looking at the vegetation index in Afghanistan and trying to derive information about food access or food security, you're not going to get any information. Just hardly surprising for those of you who know anything about Afghanistan, but it's important to know when you're doing this kind of analysis. So to conclude this section, the consequences of being integrated in the economy is that, in the international economy, is that these extremely high food prices are felt by local consumers. They're eating the food that we are producing, which means that our agricultural policies make a big difference. What we do with our ethanol and how we drive our cars impacts these people in these very poor East African and Central Asian countries. In West Africa and Southern Africa, they are not integrated, but they also have a much more difficult time when they have droughts accessing food, which is why we end up airlifting food into Niamey when they have big droughts, and they're surprised because there aren't very many roads, so there's a lot of issues. So when we need to pay attention to these areas, monitoring agricultural production is absolutely critical. And then I wanted to also point out that volatility, the change in local prices from one month to the next, is also related to gross domestic product. So this is the log of gross domestic product down here, and volatility along this axis. And you can see that in places with very high variability also have low GDP. Other places with low variability have higher GDP. India and China they control their market prices, so they're very smooth. But in general, this relationship is a pretty good one when you're doing economics, actually. So what this means is that it's all about development. We really need to invest in these countries. We need to invest in their agricultural systems. And we need to invest in information. We need much better agricultural systems. We need to know what the prices are locally, what the markets are doing. We need to understand what people are growing and when. We need to boost yields in good years and places with low productivity and provide support to the poor to ensure minimum consumption. That's just really critical. I mean, the bottom line is when your food price doubles and your income does not, you would be hungry too if 70% of your income was spent on food. Because there's just no, where are you going to get that other 40% of 100? You know, it's just really, really very difficult. And then too, we need to invest in infrastructure. You know, the Chinese are running around building roads in Africa, and that will have a big impact on the ability to move food from one place to another. But we need to make sure that it's in and not out, right? Particularly in these places with very, very low consumption already. And my final point is that it's poverty that causes food insecurity, not climate or economics. So we have a lot to do, and I hope that we can work together to deal with this problem. Thank you very much.
Questions? Harp.
Great talk, Molly, thanks. Are there examples of when FuseNet has actually detected an oncoming famine and then allowed mitigation to take place, and so the famine has been, the severity of the famine has been lessened?
So the question is that are there any examples of when FuseNet have done early warning of an oncoming crisis and a response has actually occurred? And the answer is yes, of course. There's lots of examples of that. One, you know, you could say that the current response in Sahel this year is a great example, not to go back 100 years, but the Sahel this year has a food access problem and a political security problem, and there's a huge amount of response from the World Food Program. But another thing to note is that FuseNet, all it does is provide information to the government. It has no stake in the game. It does not respond. It has no benefit. Or, you know, all it does is provide information to the United Nations, to local actors, regional actors, and to the United States. The agency that responds is the United Nations World Food Program, and the United States provides assistance through that, but in a different part of USAID. So it's really great because a lot of the time what FuseNet does is say, actually, the problem is chronic. You really don't, if you provide free food, you'll wreck the local agricultural, you know, or you should purchase, you can provide income assistance through cash transfers so you can support the local agriculture. It's a very sophisticated, you know, actually, and a lot of the time, frankly, what FuseNet does is advise health interventions. You need measles shots and support for children under 5, but the adults don't have a problem. You see what I'm saying? So it's really, you know, the perception that what FuseNet does is say, you know, let's dump corn from Kansas there. No, I mean, it's actually a very nuanced and complex answer to a nuanced and complex problem. Yeah. Mm-hmm.
Now, are you referring to remote sensing approaches or to more on-the-ground information about production?
It's on-the-ground information about production in areas that are, oh yes, so the question was, is monitoring, why do we need, or the question was, when I was asking for more information about agricultural production, what kind of information is needed? Is it remote sensing or otherwise? And what we need is better agricultural statistics. So what FuseNet has actually started spending several $1 million a year doing 1 meter and 30 meter cropped area assessments in countries with high amounts of food insecurity. So Ethiopia, Zimbabwe, Niger, and Haiti have been done. And what they find is that the local statistics produced by these countries, whose governments aren't particularly good at statistics, as you might imagine, and spend almost no money on agricultural assessment, have really bad statistics. So not only do we not know the yields, but we have no idea which of the fields on the ground are being planted in any one year and which ones are not. So, and we don't know the total production either. So there's a huge, you know, with 30% difference between two agencies in Ethiopia, the statistical agency and the agriculture agency, a 30% difference. That's a huge amount of food. And the implications of those, and of course, the assessment that we did showed, or the FuseNet partner that did this, it was in the middle, of course, but both of them were wrong. And so it's really hard to explain to people who don't work in this arena how incredibly unreliable the statistics are in these countries. Many of the agricultural yield estimates are done by one guy in a Jeep who drives around to all his friends for 1 or 2 days and says it's 20% of last year. I mean, that is the assessment, and those are the numbers. And you just take last year's number, you whack off 20%, or you add, and that is the assessment. So it's you know, the world is a big place. We do a lot of different things. It's very complex, and now that we have 1 meter, wall-to-wall, 30-meter free data, daily MODIS at 250 meter, and we should get the statistics that we need to transform that data into information that we can use to help people. I mean, that, without the ground, so my example that I showed in Australia would never work without fantastically high-quality yield information from Australia. We don't have it in most of the developing world. Any other questions?
Other questions?
So,
All right, thank you very much.
my pleasure.
Okay, our last speaker this afternoon is Dr. Avner Vengash. Dr. Vengash's research is focused on 3 major areas: the energy, water quality, health nexus, including the impact of shale gas drilling on the quality of shallow groundwater and surface water, water quality and deterioration of water resources and impacts on development and health, such as the coastal aquifer of the southeast United States, and finally, the occurrence and impacts of naturally occurring contaminants on human health in different aquifer systems worldwide. Dr. Vengash wears many hats at Duke University, including the professor of geochemistry and water quality at the Nicholas School and professor in the Department of Civil and Environmental Engineering. His presentation today is entitled Environmental Consequences of Past and Future Energy Production in the United States.
Thank
Dr.
you.
Vengash.
Thank you. Just if you can find it.
Oh, okay. Is it on that screen there?
I trying to see that. I loaded before.
Is that it?
No, is this mine? I'm not sure.
It could be.
Can I try it?
Yeah, go ahead. Yeah, that's yours.
Yeah.
Cancel
Yes.
that.
Got it.
Right there.
Right. Thanks.
There you go.
Thank you, Dave, for inviting me here. Thank you all for attending today afternoon and coming to this session. Before I start, I would like to acknowledge my colleagues and my students at Duke University who are part of this story. First, my student, they're more important, as you know. I would like to acknowledge Nat Warner, Laura Raoul, and Brittany Mirola for their participation in the study, and also acknowledge my colleagues, Rob Jackson, Tom Dara, Rich DiGiulio, Helen Sukim, and others at Duke that are part of these different studies that I'm going to show you today. And basically, I'm going to talk about the energy-water quality nexus and focusing on 2 themes or 3 themes related to coal mining through mountaintop mining, coal combustion, and shale gas exploration and hydrological fracking. And basically, the major 2 players today in the energy production in the United States are coal and natural gas. There are other factors that playing a role in the energy, but I would like to focus on those major 2 things. And basically, if we look at the evolution of energy production in the United States, we see that we are kind of in a very interesting phase in which the first time in decades natural gas exploration exceed coal production. And this is just because of the very rapid growth of shale gas production, and I'm going back to this later on. So those two components in energy production in the United States are the core energy kind of security factors, and many studies have looked at different environmental consequences of those development, and I would like to highlight the effect on waters, and that's kind of the major themes in my talk. Also, I'd like to mention that when we're looking only at electricity production in the United States, coal still constitute about 42% of the energy production for electricity per se. So it's a major important thing. Normally we think about coal as something of the past, but coal is part with us, is part of our present and also the future. And what does it mean? And I'm going to talk about, when we talk about the roadmap for clean energy, clean coal, you know, it was mentioned numerous times in the election recently, talking about the clean coal. What does it mean? Does it mean in mountaintop mining, where we have, I'm going to show you evidence for stream accumulative contamination by salinity and selenium? Does it mean that when we use the coal, when we combust the coal and generate coal combustion product, what's happened to those coal ash when we deposit it into a coal ash pond? And I'm going to show you that there is a severe contamination of the environment, and even this contamination becoming much more enhanced when we install scrubbers to protect contamination of the atmosphere. And also the future, talking about shale gas and hydrological fracking, there are of course economical advantage to that, but there are also environmental consequences, and I'm going to focus on the water quality, talking about a contamination of stray gas and also disposal of produced water from shale gas wells. Let's start with mountaintop mining, and an example for West Virginia. And this is one of the most pristine, beautiful places in the United States, which has turned to have a major change in which mountains are turned into landfills due to the operation of surface miners for coal. Here is just an example near a Hobbit mine in West Virginia. We can see the landscape in 1984, moving to 2009. We see that most of the area turned to be used for mountaintop mining, and we focused our research conducted at Duke University at Mud River in this area that you can see here in this area. And what this is a zoom in into the area. So you wanted to have a look at the difference between reclaimed coal mine that is not active anymore to active coal mine here. And we kind of wanted to see, if you stop mining, what's happened after 20, 30 years? Is it still effective? So we sample streams that coming from the watershed in the reclaimed coal mine, and also stream coming from the active coal mine of today, and also measure what's happened into the river that along the flow in this watershed. And what we've seen in a paper that was published last year in the proceeding of National Academy of Science by Ty Lindberg as the first author, we saw that if you look at the river, and this is a kilometer distance from the pristine environment without any effect of surface mining, we see the rise of the salinity of the river at different times of the year. And so we see the spatial and temporal variation of the salinity by measuring electrical conductivity. And here is reinforcing the EPA regulation to limit discharge of effluent less than 5 microsiemens per liter. And that our data can reinforce that this is a very wise thing to do. And also, if we look at the selenium data, which flowing into the river, we see the rise with flow from a very low background level of almost 0 to high level exceeding the ecological threshold of 5 parts per billion. So we see the effect taking place in the system, and we also see the effect on the biological system, as there are many evidence of the formation of the fish in the area of downstream from the valley fields, which generate those effluent. And in our study, we also not only showing the rise of the selenium, we also calculate the percentage of the watershed that being affected by mining, and we see there's a very nice linear correlation between the distribution, the area distribution, to the actual concentration of selenium in the downstream river. So there is a really kind of a linear correlation. The more you would mine, the higher will be the level of selenium in the water. Now, we found also that there is a very nice correlation between the selenium content to the strontium concentration in the water. So the strontium is very good, would be a very good proxy for the level of selenium in the water. And when we're looking at the isotopic fingerprint of strontium, which we like to use different isotopes as a tracer for sources, we see that those effluent that coming with high strontium and also high selenium would have a very different isotopic fingerprint relative to effluent that affect the river with much lower concentration of strontium and selenium, but very different strontium isotope composition. So for this relationship enable us to tell sources of selenium and discriminate between cases that we see just simple dilution of selenium in the water to actually different sources of selenium. And we're doing this approach to also to use it for establishing geochemical isotopic tools, including strontium isotope, carbon isotopes, and sulfur isotope as a proxy as a new diagnostic tool to delineate contamination processes associated with mountaintop mining. The second research that I would like to report to you would be the effect of coal combustion. And this is a map of about the 500 power plants distributed in the United States, which generate about 130 million tons of coal ash every year. And the coal that we are using was generated in a swamp, as you all know, hundreds of years ago. And this anoxic environment of those swamp contaminants like arsenic, boron, selenium, and strontium were being accumulated in the organic matter into the mud that eventually evolved into coal. When we combust the coal, those contaminants will be volatilized to the atmosphere and will be retained, however, by the fly ash that is being residual during the combustion. Installation of scrubbers like desulfurization to remove those emission of particulate and gases like sulfur to the atmosphere, causing retention of those contaminants into the coal ash. And when we store it into coal ash ponds, we will generate leaching of those contaminants, and if they're located next to a lake, those contaminants go back into the water. So we see recycle from the old swamp that we talking about hundreds of millions of years ago back to the water today. And we are making those recycle. And in a study that published on Monday, we show systematically that all of the sites located downstream from coal plants in North Carolina are having different level of contamination. The effluent, this is an example in Hyco Lake in the northern part of the state. We can see, just for an example, elevated level of arsenic in the effluent that discharge from the coal ash ponds. And then we examine what's happened to the lakes and what's happened to the river. And we found two types of behavior of contaminants. On one type, here as an example for boron and for strontium, we found that those contaminants behaving conservatively with the water, meaning if you have dilution, the concentration will go down. So it's a kind of a very simple understanding of their behavior. Other elements like arsenic, manganese, and barium are much more sensitive to the redox condition in the lake. And during certification of the lake, during the summer, when we have thermal certification, the bottom water becoming anoxic, as you know. And what we have found that those elements are actually released to the water. So we also found that we are high concentration of arsenic in the pore water that are extracted from the first 10, 20 centimeters at the lake bottom. So we established a model that we basically, arsenic is being retained by particulate matter in the lake water. This deposited to the bottom will cause accumulation of arsenic that under reduced condition, like during certification in the summer and or during burial as the first upper sediments in the lake, would release arsenic to the pore water. And indeed, we found very high concentration of arsenic. You can see those, this is in pore water or interstitial water, even exceeding the EPA criteria for ecological threshold, definitely exceeding the drinking water regulation. And this is where we think the biological triggering of bioaccumulation of arsenic will start, and from that point at the bottom, at the sediment bottom. And the problem is not only North Carolina. This is the map of all the coal ash ponds taken from the EPA database, and we see almost about 1,000 ponds distributed everywhere in the country. Almost every state will have those ponds that will affect the water quality. And the last part of my talk, I'm just giving you some highlights of our studies. We'll talk about the shale gas drilling and hydrological fracking. This is kind of an image of a drilling site in Montrose, Susquehanna. And basically, if you are living there, this will be your next door neighbor. And you have to accommodate living with such a neighbor, which is not very quiet neighbor. There's a pretty much noise associated with that, not to mention about hundreds of trucks coming in, coming out. So it's a huge issue and a huge environmental, social, economic consequences about that. So probably this crowd, we don't need to talk about what is hydrological fracking and shale gas drilling, but just in a nutshell, we're talking about drilling a few kilometers in depth into impermeable layers that previously were not able to use for exploration, and injection of high volume of unknown chemicals, what we call the fracking fluid, plus sand in a high pressure into horizontal drilling, cause it opening the fractures and release the methane that being entrapped and into the wells and pumping it to the surface. And the question is, why it's so important? Because it's here and it's available. This is the map of the shale gas basin throughout the United States. The Marcellus Basin is the most larger one in the northeastern United States, but the Fayetteville, the Barnett, and other basins are as important and are being used extensively. We can see here the rise of shale gas exploration in the United States from almost nothing in early 2000, and the mid-2000 is jumping and accelerate exploration to currently about 20% of the natural gas exploration, and going to be in 2 decades about 50%. Here you see the absolute volume, and here you see the fraction of the natural gas in the United States, and about 50% going to be in 2 decades. The importance of shale gas, China, Australia, New Zealand is not in the map, Germany and Poland, those are the countries that are going to start shale gas drilling and hydrological fracking. Some countries like France, they have it, but there is a ban on that. So one of the important things, what we are going to decide how to handle and to manage shale gas exploration in the United States, going to have a huge implication for the rest of the world, because they're going to follow our example, whatever it would be. So in many countries, shale gas is about to begin. There are some exploration in Germany, in Poland. So we expect that the next years or so, this is going to rise and expand it as well. So we know this is not a very simple question. There's a lot of controversy about that. So I will tell you about some studies we've conducted based on we collected about 300 by now private wells in areas, mostly in northeastern Pennsylvania. Now we're expanding also to New York, and we also expanding a bit, starting to work also in West Virginia, and we also work in Arkansas outside the map with the USGS. So we're trying to build a database, which is unfortunately lacking, to establish understanding of the water quality that associate with shale gas and hydrological fracking. Our first study came out last year and published in the Proceeding of National Academy of Science. And in this study, we showed that shale gas wells, private wells, located less than 1 kilometer to the nearest gas well would have higher probability to get high methane in the well. So having high methane, meaning that the level of the methane exceeds the saturation, and if you lit the water, it could be the water be on fire, and that's the way, for example, the local people in endemic areas sitting overnight and watch the water burn on fire through the night when the water becoming super saturated with respect to methane. And this is the line over here. And since the publication of this data, we have many more data points to support this relationship. And we also found that those well located near the nearest gas well have also distinctive isotopic fingerprint. So when we're looking at methane isotope, we use carbon isotopes, and we also use the ratios of the hydrocarbon to distinguish between thermogenic methane that originated from a shale gas generation, and the values of shale gas are here, versus biogenic methane that can be generated in relatively shallow aquifers, as you all know, and it would have much more negative carbon isotope ratios. It would have also very high different ratios of the hydrocarbon themselves, and we found that those wells with the active close to the shale gas well have distinctive isotopic composition very similar to the actual producing well versus those located away from the well, which have some much more mixing relationship between biogenic and thermogenic isotopic fingerprint. Why we have stray gas contamination? There are two major explanations, and this is taken by a cartoon from the Scientific American magazine. One would be release and escape of methane from leakage in the casing because an improper installation of the casing. And in this case, the methane will be escaped and will be distributed within a fracture permeable zone of the aquifer. Another possibility is that the methane will be escaped from the actual target formation at depth, somehow related to the fracking and will find its way up to the surface. We think that the first option is more likely mechanism, which I think is a good news because it can be fixed. That it's because if this would become the mechanism that is actually controlled, this will be inherent problem of hydraulic fracturing, and it's most likely that we see failure in the casing that would enable the methane to escape and reach to the shallow aquifer. In our study, we didn't find any contamination of the dissolved constituents in the water. And that's very important. We actually showed that none of the water, even if we have a very high methane, they don't have a high concentration of salt or radioactivity or other things that could be associated with fracking fluid. So we see some contamination of stray gas. We don't see contamination of dissolved constituents in the water. The second paper came in July this year, and in this paper we expanded the sampling and we looked at different aspects. What we found here, we found that wells located in valleys in northeastern Pennsylvania, but not only, have water that is relatively high saline and have a very unique isotopic composition. And this is the composition of the water that we found, marked in red in the previous slide. And if you're looking at different constituent, here's chloride compared to bromide, for example, which is considered as another conservative element. We see a very simple mixing relationship between what we found in produced water in the Marcellus brine and the shallow groundwater, and those type D, what we call water, is the saline water that lying on a mixing line. What we did also, we took all the water that could get access, produced water from the different formation in the Marcellus, but also in the Utica and other formation, and measured the strontium isotope composition of those produced water. And we found that the shallow produced water from conventional gas in northeastern Pennsylvania have very different isotopic fingerprint relative to the Marcellus. And the water, type D water that we measure, are very well consistent with the Marcellus isotopic composition. So if you plot it here, you can see the strontium isotopic ratio versus concentration in logarithmic concentration of strontium, and you see that those red spots are those saline water, and if you do mixing calculation for those two populations, you see they would mixed with the Marcellus brine and would be very different from the upper Devonian produced water that could be a source. From us, we mean interpreted this as hydraulic connectivity between the Marcellus brine and the shallow aquifer. Now, we have data from the 80s, only the chemistry of the water, that we already see those saline water. So we're able to exclude the fact that this is a new phenomenon. This has been, at least from the 80s, having the similar composition, and we also did not find geographical proximity for shale gas site like we found for the methane. So we exclude the fact that this saline water derived from active shale gas exploration and hydrological fracking. We're saying this is a natural occurring phenomena. However, from this indicate that there is hydrological connectivity from depth into the shallow aquifer. So if there is a leakage somewhere in depth because of the fracking, there is a potential of brine to flow through the system. We're talking about an open system rather than a closed and separate system. That's one of the conclusions of this study. And finally, just to touch it, to talk a little bit about produced water disposal. And the question, does disposal or produced water disposal cause long-term ecological effect and health risk? What's in produced water? So the water that's coming together with the gas is not what water we put in. It's actually the natural occurring formation water that are being part of the Marcellus and other shale gas formation during geological time. And they're characterized by very high salinity, the TDS up to 250,000 milligram per liter, 10 times the salinity of seawater, very high level of bromide. This is a big issue for people in Pennsylvania because high bromide in water, even if you dilute the water significantly, you were still having residual of relatively high bromide in fresh water. When you take this fresh water into drinking water and you treat it, you chlorinate it, you would generate a carcinogenic disinfection byproduct like bromide trihalomethan when you chlorinate the water. So this is a big issue. There's also a high level of many toxic elements associated with that, and also very high level of natural occurring radioactivity, which is very carcinogenic as well. So we went to West Pennsylvania and sampled the water that's coming from the pipe, and it has salinity of about 200,000 milligram per liter, relative to about 100 milligram per liter that you know will be any nice streams in Pennsylvania. We see that this is a chloride in logarithmic scale versus distance from discharge. So this is the zero discharge point. This will be the background that I just talked for the chloride. And we can see that up to about 500 meters downstream, we are creating a dead zone of very high salinity. And I think this audience, you don't need to explain what's happened to the biological system under this type of level of salinity. Even more when we actually collect the sediments that are in the river, we found that those sediments accumulate the radium that coming together, the radioactivity that coming together with the disposal water. And we see, it's still preliminary data, but we see that it's extremely high level of radioactivity in the sediment, meaning that we are talking about a legacy of contamination that's going to stay with us for generation, and radium known to be bioaccumulative as well. So if there will be any life there, they will be affected by this high level of radioactivity. So in conclusion, there's no clean path for energy security in the United States. The energy sector still depends on coal and continue to be so in the next decade. And the new game changer is indeed shale gas extracted through hydrological fracking. We think, we're not very objective, but we think we have a solid scientific studies that showing that coal mining, coal combustion, and shale gas exploration using hydrological fracking would have significant consequences on the environment. And in many cases, not always, but at least for shale gas, it's still unknown. But for coal, I think we are much more in a better shape of understanding, would contaminate the water resources in the United States that located downstream, either from mining sites or from disposal of coal ash ponds. And I think it's important for the decision maker to understand that low-cost coal and the new shale gas reserve in the United States are vital for enhancing U.S. energy security, but we do see evidence that direct and indirect effect on the environment have significant long-term implication for the ecological system and human health. And this kind of should be part of the balance. Just to slide to finish, there are more. This is the reference for the different papers that I mentioned. You can download them from this website that if you are interested here. And also, we received some funding from NSF for the geobiology and low temperature geochemistry program to conduct a workshop at Duke. It was done in January 2012. It's a typo here. And you can see if you go into the website, that you can see some of the lectures talking much more further what I talked today, talking about the different aspects, the social implication, and the debate about shale gas and hydrological fracking. Thank you very much.
Any questions? So I have one, and I may have just missed this, but why do you think that the methane entering the groundwater is coming from the casing?
Okay, so we have several explanations to that. First, we have more data to support that by using other tracer that hasn't been published. Second, we think that the likelihood of migration of the gas, it's about 2 to 3 kilometers from the shallow aquifer, is less likely than leakage through casing. But the truth is that we need systematic, as we say, we need information. We do need information about the environmental effect, and I think those studies are only the beginning to have much more comprehensive database. And I think it's very early now to determine if we really know the mechanism for contamination.
Lindsay.
Have any state or federal regulatory agencies been sampling water quality issues associated with brine water? Or is it just not been a question that's come up up to this time?
So the question was if any state regulatory doing sampling of water in areas of shale gas development. You refer to shale gas, not for coal.
No, the brine water is
So yes, so as you know, I think it was Cheney was in the Congress, was the shale gas exploration had exempt from the regular Drinking Water Act. So there's no any systematic monitoring nor regulation for disposal of the produced water in the United States right now. I know that the EPA has conducted a study of the environmental effect, and they are right now doing their study, what are the environmental and water quality issues taking place. But as far as I understand, there's no any regulation. There is some state regulation. So for example, when the level of bromide in Pittsburgh reached to the level that trihalomethane becoming much more frequent, there was a local decision to start to move those produced water to Ohio rather than dispose it into waterways in Pennsylvania. And then they actually recharge into deep recharge wells, which is one of the way to get rid of produced water. Now, that could be great because you take the produced water and back to the geology. However, it was suggested that several of the recent earthquake, like Youngstown in western part of Ohio, were directly related for the injection of those produced water. So, so that's kind of the issue. So my understanding that there's only local state management or regulation to deal with it, but there's no EPA kind of regulation, and it does not meet, of course, the Drinking Water Act. You wouldn't allow disposal of 100,000 milligram per liter brine just to be disposed to the environment.
In the 1980s, we live in Alabama in the Black Warrior Basin, so in the 1980s, there was a tax subsidy for companies who were searching for and extracting coal. Then it was called coal bed methane.
Which, right.
Is there new technology for this latest round, or is it still the same?
Well, coal bed methane is totally a different method. The question was about the coal bed methane in Alabama. And so coal bed methane it has been before the growth and exploration of the shale gas, and it's a different technology. It's much more shallow, and it's the technology of extracting it is much more different. This is a methane that generates associated with the coal. So it's totally different source of methane. It's much more shallower, and it has different environmental implication. And I think the similarities is that together with the coal bed methane, you generate formation water, and what do you do with the disposal of that? That's becoming, there are, of course, similarities in that.
Any other questions? Thank you.
You're welcome. Thank you.
So at this point, I have lots of thank yous, but before I do that, I want to turn the floor over to Jay Arnon, who's, we're going to have a couple of what I call flash presentations by some of our colleagues in the funding agencies to tell us a little bit about what's going on there over the next year and what they're seeing happening. But before I do that, I do want to make one thing clear, and that is that we are very, very pleased and we thank all of our speakers very much for spending the day with us today. I found it very interesting, and I hope you all have too. Jay?
As Dave mentioned, my name is Jay Arnone. I'm also on the board of the Association of Ecosystem Research Centers. I too would like to thank again the speakers for fantastic presentations today. I had learned a lot. I hope you all did too. Because one of AERC's major missions is to communicate the importance of ecosystem research to the public policy discussion through events like the briefing this morning and the symposium this afternoon, it's equally as important to have a discussion about how that research is supported. And we've developed a tradition every year to invite program officers, program managers from federal agencies, funding agencies that support ecosystem research. And we have two speakers today, We have 15 minutes for this part of the presentation, so don't panic. Each of the speakers will have about 5 or 6 minutes to share with us their current programs that may be relevant to ecosystem research, as well as maybe giving us a glimpse of what's coming down the pike in terms of programs they're discussing at the respective agencies. The two speakers today, one from the Department of Energy's Terrestrial Ecosystem Science Program, is Dr. Dan Stover, and from NSF's Division of Environmental Biology and Emerging Frontiers Programs, Dr. Henry Goals. And they will share with us for a brief time and leaving some time for questions at the end some of the programs they've got on the docket right now and what they have in the offing. So Dan, you want to start? Okay.
Oh, you have some slides? Yeah. Put them right here.
Henry, as I load this up, if you want to go, I don't know if you have slides or anything you want to pull up, but if you want to go while I load this up, and that way we won't keep anyone behind.
There we go. Yeah, go ahead, Henry.
Okay, yeah. Hi. I appreciate the invitation to be back here. I'm not going to go through programs, but let me just say a couple of things, hopefully provocative, and then if you have any questions, we can talk, offline or in the discussion. One is that, as this symposium showed, and as if you've been involved with the NEON discussions over the last day or so, and paid any attention to any of the news in the world, I think that the demands for ecosystem science writ large, interpreted more maybe as environmental science or something, are probably are greater now, no question they ever have been. I mean, we're living in really uncertain, fast-changing times. And so in that context, there's two things I wanted to mention particularly. One is that the Ecosystem Science Program at NSF has provided some funding through the Carey Institute for running a series of workshops at meetings called Frontiers in Ecosystem Science. I think they're doing 8 meetings, or going to 8 meetings. I think 4 of them maybe have occurred. I'm going this weekend to the Soil Science Society meetings in Cincinnati. Maybe I'll see some of you there, and I encourage you all to look for these sessions in the programs of meetings you're going to. There'll be one at AGU, for example, ESA next year, and then another couple coming up this winter. And the NSF Ecosystem Program officers, at least one, are trying to be at all of these. And they've been really, really fascinating sessions. A lot of soapboxes, 2-minute soapboxes for people to come up and give their impressions of where's the field, what's the field right now, or where is it going, and what things are exciting. And it's really very cool. At the end of this, the organizers, it's Peter Groffman and Kathy Weathers with a much larger organizing committee, will be convening a workshop and then producing, a Frontiers paper or something, talking about the findings. There's polls and all kinds of things you can fill out and all kinds of ways that you can contribute, but they're basically open sessions to get as much input as we can. So I really encourage you to participate in those and look for them. Second thing is that, given all the issues and importance of ecological issues, again, I think that at NSF, certainly, there's probably more opportunities for support than there ever have been. Okay, that comes with a couple of caveats, obviously, but one addition, for example, I talked about yesterday at NEON was the new macrosystems biology program. This is a new $20 million a year to support ecological sciences at regional continental scales. That's going to go on for at least a few more years. It's in the Emerging Frontiers Directorate. And then also in what we call the SEAS portfolio, which other agencies are participating in also. This is the sustainability program. So there are like 13, I think, initiatives now at NSF. And these are cross-directorates, so they bring in social sciences, engineering, biology, geosciences, and so on in various combinations. With certain foci, like relatively new ones would be, there's a coastal initiative, an Arctic initiative now, and then there are also things called sustainability research networks, which are very large, sort of modeled after our long-lasting RCNs, which are much smaller, research coordination networks, but these are massive. But so it's sort of taking the coupled natural human systems program, which some of you may know is a core program at NSF, and really cranking it up a level. So this is not all new money to NSF, but it's repackaging money, some new money taken from other areas. But it's just these are just all examples. If you look through our portfolio, that you'll be really amazed at the opportunities. Caveats, of course, are pretty obvious. We're in a highly uncertain times, and that applies to the NSF budget as well as every other federal agency's budget. There's 2 big dates coming up, November 6th, which will then lead into January 1st, which is the fiscal cliff. And as part of that, we've been told to plan for a 30% cut in travel, independent of these other issues, precipitated by the scandals last summer and fall. If that happens, you can imagine how difficult it will be to operate. So, these are highly uncertain times. So there's good news and there's bad news. And the other caveat, of course, and I'm sure Dan will talk about this a little bit, is the R&D portfolios and the other agencies, particularly the other natural resource agencies, the ones that have applied missions, continue to decline. So, NSF's budget hasn't gone up. We've been maintaining, but it's very uncertain. So if you have proposals in, you know, or you're going to be submitting any soon, you know, your notifications and things are probably going to be delayed somewhat this year because, you know, we just really don't know what we're facing here. So very interesting, challenging times, you know, in the community, in the world, and in the universities and in our agencies. Do you want to take questions now?
Sure.
Or okay. Art?
Yeah, given these uncertainties and what the future seems to hold, what's your crystal ball tell you about the importance of broader impacts of proposal versus intellectual merit?
Well, at NSF, we learn, at least at the program level, not to invoke crystal balls, but well, this has been a very active discussion area all the way up through the National Science Board. National Science Board sort of punted, you know, on it really. They said, yeah, it's very important, we need to do more. You know, I think in the ecological sciences in general, it shouldn't be very hard these days to write a convincing broader impacts section of a proposal. Almost anything that we do, certainly coming into ecosystem science, is embedded in climate change and, you know, a lot of other issues. And so, you know, articulating that is a challenge, but, you know, that's a broader impact, and, you know, you can count that. It doesn't have to all be, you know, recruiting minorities and you know, doing all kinds of wonderful new education things, although we also welcome those. So, you know, to me, it seems like, you know, we're on the one hand, we're trying to raise that bar. PIs are getting it, reviewers are getting it, you know, just the standards are going up for the broader impacts. But I also think certainly in ecosystem science that everybody ought to be able to articulate the impacts to society of that science without a lot of problem. And if they don't, I'm not going to have a lot of sympathy for them.
I agree totally, and everyone ought to be able to articulate that. I'm just concerned about the 15-page limit and repackaging a proposal to increase your detail in the broader impacts.
Yeah. No, that.
From the other parts.
Yeah. No, that's a very good point. You know, we've also changed some procedures I won't talk about, but you know, NSF is not a uniform agency, contrary to most people's ideas. So we've just gone in bio and our core programs to pre-proposals. You know, so you only have 4 pages, and so to get over that first hurdle, you really have to be concise and convincing. You know, in both the scientific merit and the broader impacts. But we hear what you're saying, and it's a concern.
Talking about the pre-proposals, I know there has been some sort of a revolution within the science community about that. Is that something that is going to continue to exist? Or
Yeah, this is a huge issue, and one of our challenges, and one thing we didn't do very well on, was communicating with the community when we were leading up to these changes. The feedback we've gotten has been highly mixed. I would say in general that people are in favor of some kind of pre-proposals versus writing big proposals all the time. But, you know, how we do it, whether we're, you know, the numbers of deadlines, the numbers of pre-proposals you can be on, all those kinds of things, so it's all up for discussion. But we had to already last month decide whether we were going to change the solicitation for next year, because just that, you know, because it takes months, you know, of deadlines to in advance, you know, to do that. And the decision was made to not change it for next year. Okay, so what the solicitation said last year will apply to those programs that are affected. And again, in the sort of ecological sciences, there's a lot that aren't. Geosciences isn't affected by what we did in Division of Environmental Biology. The macro systems program isn't in there. You know, so it affects a set of programs, but not all of the programs you would consider anyway. But we're working on that, and the first thing we're trying to figure out to do is how to channel all that feedback from the community and how to, initiate that dialogue and discussion and keep it going and have that bear on what we finally end up doing over time with the solicitations.
Henry, NSF has a remarkable history of holding to its commitments once it makes an award. But if we go into sequestration or something like that, is there any chance that continuing awards might be reduced?
I would say it's virtually nil. Oh, I'm sorry. Yeah, the question was, sorry about that. The question was whether if we went off a fiscal cliff, what we would do in terms of continuing awards. That I think that would, the glib answer is that would depend, on how bad it is, obviously. But in general, when we've had restrictions in the budgets and things, we have stayed with our commitments to existing awards and just made fewer new awards. Right now, we're operating at about 75% of our, last year's budget, which is why I said that there's going to be a number of decisions that are just going to have to wait until the spring because we just don't know, what we're going to have out there.
Can I ask a follow-up question on that? So if there are proposals pending and you can't turn around decisions before December, that impacts the next.
Well, certainly. No, but up to the whatever budget we have in our hands, we can make commitments, and we'll do that. We're not going to delay all of our notifications and awards and things. But there's going to be some that are going to be, down a little bit on the list that we really want to fund, and they're going to be the next ones to be funded, and presuming that we get that money back or something in the spring, or the cliff, turns out to be a bump in the road or something, then we'll go to those and as soon as we can, and we'll be in touch with the PIs about that.
Okay. Well, if proposals are in that sort of bin, would you recommend or allow submitting another pre-proposal, or would that obviate any pending proposal?
Good question, because the next deadline is January 9th, right? So for those programs that are affected, so. Yeah, if we're not notifying you, we're not penalizing you.
Okay.
Yes. Yes.
One more question.
Okay.
So have you seen today that ecological sciences is becoming much more interdisciplinary and much more diverse than the traditional ecology? Are you, in terms of proposal, kind of aware of that and would accommodate projects that are touching the broader sense of ecology?
Well, the programs, the SEAS programs are definitely, and things like coupled natural human systems, they're mandated to be broad. You've got to address, they have to be interdisciplinary by nature. To the ecosystem studies program, we've always viewed that as, sort of a core, but with a lot of relationships around the outside. We co-review typically about 40% of our proposals. And actually, most of those are, not surprising, with the population community ecology program. But outside of that one program, most of them are with various programs in GEO, for example. So. But also social science and other places. Okay.
Henry, thanks for coming.
Sure.
We appreciate it. Yeah.
Right. So, for whatever reason, I came with a presentation, so bear with me here. I'm going to skip through some of this because just in the Department of Energy is made up of 6 different offices. We're the largest funder of physical sciences in the country. One of the offices, which is the office I lie in, is the Office of Biological and Environmental Research, or we just call it BER. And one of our primary goals in BER is to understand the potential impacts and effects of greenhouse gas emissions on the environment. So that's where my program, Terrestrial Ecosystem Sciences, come in. An important thing to discuss is this year, just a couple of months ago, we released our 5-year strategic plan for the Climate and Environmental Sciences Division within the Office of Biological and Environmental Research. And again, building within this, and you can find this on our website here, within this, I think it very clearly states what our mission is for our particular division and the programs which lie within that division. And it's to advance a robust predictive understanding of the Earth's climate and environmental systems and inform the developments of sustainable solutions to the nation's energy and environmental challenges. So again, my program particularly is TES, or the Terrestrial Ecosystem Sciences Program, and we are tasked with doing foundational science to improve our predictive understandings of terrestrial ecosystems in the context of climate change. And we do this through a number of different mechanisms, through observations, manipulations, large-scale long-term field studies. FACE is a good example of the type of work that we've done, and Ameriflux is another one. But it's important that you note that one difference from the programs that our predecessor programs into what we've become now is that this process modeling and the research we do has very strong ties to Earth system models. So we do provide funding at roughly the 50-50 level to the universities and the DOE national laboratories. This is what's happened over the last 2 years in the program. Last year in fiscal year 12, well, I guess in the current, well, I guess now technical, last year, we did have a solicitation out for about $3 million. We did receive 200 pre-applications. Of that, we encouraged and then received 140 applications and made 13 awards. So it's a tough world out there, but the big challenge is our budgets are not going up. Our budgets are, if we're lucky, are staying flat. Flat is the new up. So, but within that, you can see that we highlighted a couple of new areas for our program that we're growing into. We've had existing programs in natural disturbances. We've added below-ground ecology, which is my specialty, coupled by geochemical cycling. And we've highlighted two new geographies of interest. This was the Arctic and the tropics. And then we've just released back in July our fiscal year 13 solicitation, roughly again at $3 million. The pre-applications were due in September, and the full applications are due next month. Again, we've highlighted below-ground processes again, which you'll see as a specific highlight in our strategic plan. Again, our two critical ecosystems, Arctic and the tropic. We've also added one which you can read into this as our interfaces, our terrestrial process interface. In this case, we looked at aquatic interfaces, so particularly we were interested in methane and wetlands. We've added disturbance, and we also went in with one of our other programs in our division, which was the Earth System Modeling Program, to do some community land model developments. So we also have a number of laboratory programs at our national labs, which we collaborate with, encourage to collaborate with the universities, Argonne, Lawrence Berkeley, Oak Ridge, Pacific Northwest, and LANL. And I'll talk a little about these other programs. And much like Henry said, we do try to get out to the community so that it's just not that when you come to DC you get to meet us, but we try to get out as well. But again, with budgets going down and our reduction in how much and when we get to travel, it's getting more difficult. But our two meetings that my program we do attend are the AGU meeting and ESA. So if you're at these meetings, I encourage, a lot of times the town halls are at weird hours, but I encourage you to stop by and see us because it's a great way to bounce some ideas off of us and hear where we're heading for the next year. I want to take a couple of quick minutes to talk about the big efforts or big emphasis on our program. And the first one is NG, which stands for the Next Generation Ecosystem Experiment. NG has this weird history of becoming, it was originally designed to be the second generation of FACE, but it's through the years and different program managers and priorities, it's changed a little bit. Now it's really focused on process representing these critical ecosystems in Earth system models, less so on the manipulative experiment side, although there's a considerable amount of field research that goes on. And again, the NG, the first one we've selected will be in Arctic. It has two field sites currently, one in Barrow, Alaska, and the second will be at Council, which is on the Stewart Peninsula. It creates a nice space for time transect that we can look at for changes in permafrost. So I've got a couple of flyers in the back that if you want more information on NG Arctic, but this is a 10-year effort. DOE takes pride in its long-term efforts for these research programs. It's $10 million a year for 10 years. We're spinning up a second one. We just did a workshop in June on research priorities for the tropics. That's so my colleague that I manage this program with, Mike Cooperberg, is leading the Arctic, and I'm leading the tropics. So we're hoping that pending the outcome of the 13 requests, that we'll have money to start initiating a $12 million project in the tropics in fiscal year 13. Our big manipulative experiment, which is in my portfolio, is spruce, and this is a climate change study. It's an open-top chamber study that's being led by Oak Ridge, Tennessee. Paul Hansen is the PI in collaboration with the USDA Forest Service. And this is in Minnesota, where they're actually creating these very large, and I think they're 8-meter tall by 10-meter diameter open-top chambers, which will double CO2 and will also have a warming, above and below ground warming sequence associated with them. This project is just in the construction phase, and I would say about 40% constructed now. They will be putting in the chambers starting in the spring. So there's a great opportunity here, and again, this is designed to hopefully be roughly an 8 to 10 year effort here to look at the responses of these northern boreal peatland, spruce peatland systems and how they will be impacted by climate change. Again, this is just kind of a high level of what we're doing and where we're going with our program. The other one that a lot of folks are familiar with is Ameriflux. We did make a $5 million award to Lawrence Berkeley Lab in June to manage the network. This will provide technical support, management support, and facility operations support for anywhere from 10 to 20 field sites of Ameriflux. And there's a whole criteria that was designed about which Ameriflux sites will be selected. And this was in response to the community coming to us and saying, you know, you have limits on how much we can propose money to your solicitation. How do you expect us to do good science when you submit a proposal just to support a facility? So we took that into consideration, and we took this program, this approach to creating a program to manage and provide the tech support to this more formalized way, and would cover the infrastructure to the long-term, high-use, high-productive data record sites to maintain these long-term sites. So this is in progress. I think Lawrence Berkeley has announced the first 1 or 2 awards that will be made to this, to 2 long-term sites. The other sites they have not announced yet, and will be announcing as they move forward through their list of candidate sites. So with that, I'll take questions. I think it's important for us to, one last thing to point out here, the website here on the bottom, the tesscience.energy.gov, is a great resource to figure out what our program is doing. We do have an annual solicitation that we're supporting. Again, like Henry said, you know, we have our existing portfolio projects, which, you know, depending on where the fiscal cliff goes, and the federal budget goes as well. We will try to ensure maintaining the current mortgages of research projects we have in our portfolio before we add new things on. But we do anticipate doing an annual solicitation. The topics within that solicitation will change from year to year. We strongly encourage folks, where appropriate, to leverage off of ecosystem research centers. You know, if there's an opportunity where something can be done, you know, why reinvent the wheel if there's a place and infrastructure exists? It just adds more value to the science dollars that we place into this. Similar to NSF, we have been doing a number of workshops. We've just did one on a strategic priority on root systems, root and below ground ecology, and another one on this model-informed research, model-informed field study research program, or what we call MODEX. So those are the two plus the tropics workshop, are the 3 big workshops that our program has managed over the last year. So with that, I'll take any general questions. I've got some informational flyers in the back too, and business cards if you want some follow-ups. But
questions?
Questions, comments, rude remarks? Nothing?
Eric.
Yeah.
You mentioned a second Arctic site other than the Barrow.
Correct.
Was it on the Seward Peninsula?
Yeah, Seward Peninsula. Yeah, it's a council. It's a small town. It's a dirt road, and you cross a river, and there's nothing there except for permafrost and bears.
Are there many people working there?
No. They've just done some geophysical surveys there right now, and the idea is that NG is being rolled out in a phased approach. So phase 1 will mostly focus on Barrow, Alaska. Phase 2 will mostly focus on Barrow and adding Stewart, and potentially other candidate sites in this time for space or space for time transect.
How does that site differ from Barrow climatically?
So I don't know, I have all the specific details to it, but effectively from what I understand from Larry Hensman, who's the chief scientist on the project, it represents what Barrow, Alaska will look like in 100 years. So it's a coastal maritime permafrost site that has significantly been impacted by warming. So these high center, low center polygons have shifted and broken apart in different ways, and there's been a lot of cryoturbulation. A lot of these processes are representing a warming treatment, basically, and what we predict will happen in Barrow within the next 100 years. So, yeah. questions? All right,
Thank you, Jim.
thanks.
So I'm the only one standing in the way of you in the reception, so, I'm sorry, what?
It's in the next room.
Yeah, right. It'll be, you go right outside the door, but not into the hall and make a sort of a U-turn. I did want to say a couple of things. First of all, I'll be stepping down as president of this organization tomorrow, and Jay will be stepping into the position. I've enjoyed my time. I rarely have the opportunity to speak with the membership, and hopefully they're watching us, so I am going to take a minute to do that and tell them that over the past couple of years, the organization has been looking for ways to maximize your return. One of the ways we're doing that is through the recording and broadcasting of our research symposium. And as I said earlier, we had a very good turnout at the congressional briefing. I want to ask members of the association to get involved, and in that respect, you can email or call any of the officers or the board members. We're on our website. The email and phone number and addresses are all there. And so I owe a great deal of thanks to the Smithsonian, and Jess, as your representative, I want you to take that to the people that have helped, and also to the gentleman in the back who manned the video and audio. You did a great job. Thank you very much. And I have an obligation also to recognize Cindy Allen, who works for me in Charlottesville, and our staff, because they've worked an awful lot over the past couple of years to make this stuff happen. Do any of the other board members wish to say anything?
Thank you for your service, David.
Well, we're always looking for ways to make things a little bit better, and we've tried some experiments these past 2 years, and I'm glad everything worked. I lost a lot of sleep last night thinking about this technology stuff. So with that, I'm going to conclude this research symposium, and thank you all for coming, and we can adjourn to the reception.
On behalf of the membership, thank all of the board. You guys did a great job here this year. This is a really important.
You know, it is, and with the election coming up, I wasn't quite sure what was going to happen, but it all worked out really well. And I actually think these are important issues.
It's really good to do webcasts.
Well, it's recorded, so we're going to start recording on the website too. Thank you very much.
All right, certainly. Thank you for your mouse. Yours, very nice.
Thank you. Do you need those batteries?
No, you have batteries, yeah. All right. Hold it.